Okay. Hello, wonderful person. I think I'm live. It's been a while. It's been a long while. I kind of forgot how to run the stream. Let me see if this works first. I'm gonna have to try to listen to myself. Also, I'm using a completely different setup from usual setup, so I'm really not used to this. But if you do hear me, please mention it in the comments. Also, hello and welcome. We might be learning about some black holes today. I don't actually know what's going to happen, to be honest. All right, let me see if the comments mention me being live, as in, can you hear me? Can you hear me now? Oh, okay, loud and clear. Let me know if it's too loud and not clear enough. Actually, the clarity, it's due to the microphone. I'm using this really cheap microphone right now because the other microphone was getting in my face and I couldn't really handle it right now. Okay, so first, let me just quickly remove myself for 1 second by doing the following and also the following. This is what we're going to be watching. I mean, technically, they're going to be streaming this, and I'm going to be borrowing their stream, and we're going to talk about this. And to be absolutely honest, I have no idea what's going to happen. I actually have no idea what they're going to be talking about. But all of the hints so far suggest that they might be showing us that image of black hole, Sagittarius A star, from the center of our own galaxy, which, if true, would be mind-blowing. But let's curb our enthusiasm a little bit. And let's just wait. It starts in I think it starts in about 10 minutes. And also, we're gonna try to just chat, talk. Maybe you can ask questions. I can answer those questions. And even though, so yeah, we hit 1 million. There's 1 million of you wonderful people, but this is not the official 1 million stream. It's just part of it. We're going to do another stream later on. I do need to actually improve my setup a little bit, and also I need to figure out a few things. I haven't really done this in like a year now, and unfortunately it's been really difficult because of the schedule and because of some things that happened to me. But anyway, long story short, this is also a charity drive, as you can probably see from the chat thingy majiggy. So any donation will go directly to Save the Children, and I've recently talked to the people from the foundation, asking them specifically to try to send all of the money raised here to the kids in Ukraine or the refugees in other countries that are suffering from the war. Mostly because, as you might have seen from one of my posts before, I'm basically directly affected by this, and my roots are in both countries, Ukraine and Russia, and I feel both guilty and heartbroken and devastated and unfortunately powerless. And so I figured, my power comes from this. Maybe we can raise money and help them. And they were very, very positive about the idea of sending as much money as possible from this charity drive to kids in Ukraine. So everything that you donate goes directly to them. And yeah, anywho, so what else? We're not going to talk politics though, so just throwing it out there. No politics, unless the politics involve some kind of alien species that we're about to discover in the center of our galaxy. No, we're not going to be doing that because the telescopes participating in this particular event do not have the capability of doing that, as I mentioned in the previous video. All right, let me just put maybe this up. Let's do some background here. Okay, cool. So yeah, while we're waiting, I guess if you have any questions that are not too extreme, not too personal, I'm totally okay answering them. Someone asked me where I currently am. I'm not actually in Quebec, even though I grew up in Quebec. I grew up in Montreal. I live in South Korea, and I've been here for a while, and this is basically where my family is now. And yeah, that's the answer to that question. Okay, lots of different aliens and Dyson sphere comments. Thank you so much for the congratulations. I mean, technically, congratulations goes to you for subscribing and for keeping in touch for so long, so many years. Some of you have been on the channel for so many years, and so thank you so much for being part of this and for listening to me ramble. We actually did a very similar stream exactly 2 years ago on May 15th, I think. Today is May 12th, yeah. May 15th of 2020. And this was when we did half of that, 500,000. So yeah, there we go. How is South Korea? It's pretty good. It's hot, a little bit steamy hot. And also there's a pollution issue here, but other than that, it's pretty good. Do I suggest studying astrophysics, math physics to the highest level? It really depends on your purpose in life. I didn't from the beginning because I didn't really understand it when I was younger. And it took my brain a few years to form enough to actually start understanding physics and math. And so then I did for fun. But unless you like it, I really wouldn't. There's not a lot of, let's just say there's not a lot of career opportunities in those particular fields unless you take them to a different direction, such as, economics or something else. But it really depends. It depends. It depends on a lot of things. Cool. Okay, let's see. What else do we have? Oh, here we go. Do you speak French? I do, enough. I actually haven't spoken French for over 15 years since I left Montreal. So if you've ever spoken a language, you know that you start forgetting things really quickly. And here in South Korea, not a lot of people speak French. And also most people try to speak to me in English because they're trying to practice English. So I kind of forgot a lot. Do I speak Korean? Not enough, no, not enough. I speak enough to order food in the restaurant, but that's about it. Good day from Adelaide. Good day to you, mate. All right, cool. What else do we have? Oh, awesome. Someone is from Syria. That's amazing. Hello to you too. When will you ship your shirts to Australia? Huh. Wait, I actually thought they are shipped to Australia. I mean, I can get them in South Korea. So the shipping part is totally not up to me. It's the service known as Teespring that YouTube kind of collaborates with. And they've been kind enough to let a lot of YouTubers use their service. So yeah, hopefully they do ship to Australia. I didn't know they didn't. Anywho, do I believe in aliens? So this is an awesome question, which I cannot answer right now because there are videos coming up. In short, it depends on what you mean by aliens, but extraterrestrial intelligence living in our galaxy, very likely no. I don't think so. At least not at this time. There are reasons I have for believing so, and I'll talk about them in some of the future videos, but statistics are against it, and probability is also against it as well. So I maybe in other galaxies far away, but let me put it this way. It's all down to one question, and it's all down to evolution of intelligence on our planet. It's a huge spoiler for the video that I'm making, but basically, if we can ever find super intelligent species in the history of our planet, we'll have a better answer of whether, aliens exist out there that are super intelligent as well. We know that a lot of things on our planet evolved several times. Things like vision, things like limbs, basically anything you can think of very likely evolved multiple times. So far, we have no evidence this ever happening to super intelligence, such as ours. I'm calling it super intelligence. We are pretty dumb in some way, but the intelligence is able to do complex stuff. And that is not something we've seen anywhere in the history of our planet, but it's also hard to find. So that is really the question we should be answering before we start looking for aliens out there. Cool. Oh, we have 4 minutes and 38 seconds left before they tell us something. I'm actually kind of curious what the picture is going to look like. I'm guessing it's going to be a little bit less higher quality than the one from M87 for reasons I mentioned in the video. It's because the motion around the Sgr A Black Hole is so much faster that there's just more blur, but they could have figured it out. They could have actually solved this. Okay, cool. Next question. Do you think humans will terraform Mars? Not really. I don't think we are going to be doing that for one simple reason. It's just, there's no point. Why would you terraform Mars? Because you know it's not going to last. We might have colonies there, but terraforming Mars is just ridiculously complex. It's easier to terraform Venus. I think we talked about this last week. Venus is way easier in so many levels, and there are so many different techniques we can use. Mars is just too small. Someone is asking me to marry them. Unfortunately, I would... in Canada, it's illegal to marry two people, and I'm already married, so I can't. So I'm really sorry. I'm very sorry for that. Very apologetic. Anyway, despite this cheesy comment. Let's go on. Okay. Okay, yeah, so someone mentions animals like dolphins, ravens, great apes, elephants. They are pretty close. They are close. Another video that I'm working on is actually, so there's a genetic component and there's an actual neuronal component to the differences in intelligence between humans and everything else on the planet. And that is actually what makes us so unique. Even if we compare ourselves to dolphins, ravens, a lot of really complex animals, there is actually something in our neurons and the way that neurons connect in our brain that makes us absolutely like on a completely different level. So as you probably know, I have a 3-year-old son, and just watching him learn and interact blows my mind every day. He's already more intelligent than any other species on the planet, except for humans, more intelligent humans. But he's reached that when he was only about a year and a half. He became more intelligent than your typical dog, dolphin, raven. He was able to solve complex tasks, but he was still growing and his brain was still developing. And, you know, after 10 years, 15 years, we still keep growing, our brains keep developing to the point where we do actually reach these really complex connections inside, able to generate ideas that no other animal is even capable of. And so very recently there was a study that discovered that animals like octopi, it's octopuses, I think that's the proper way of saying it. Anyway, octopuses, they're able to form cultures, simple cultures where they kind of live together, collaborate, compete, do things. They have little miniature like towns basically. There's a couple of them found in Australia, and the thing is, that's the highest complexity they'll ever get, at least at the moment. Their brains are just not capable of doing more, and even there, they're kind of primitive in a sense. Humans are way, way above that. The human culture is just insane. Okay, cool. Next question, or next comment, or we have 1 minute, 23 seconds. So, oh, by the way, when this starts, I'm probably going to just, stop talking, remove myself from the picture. Also, as you can probably hear, my voice is not all there. I have allergies. It's an allergy season. And we're going to listen to what they're announcing. I'm actually super curious to see what they're going to be saying. Once in a while, I'll probably come back and do a few comments, follow-ups. And then we'll see what they show us. Now, the preview here is already hinting that it's going to be a black hole, and I'm guessing that's maybe even part of the picture. But we don't know. We don't know. Maybe they'll show us nothing. They'll say, oh, hey, there's actually nothing there, and sorry, oops, have a good day. Anyway. Do you think if aliens showed up, they will be friendly or harvest the planet? I mean, I don't think they'll show up. I really don't think they'll show up. I don't think there's a point. What's the point of coming to this planet, first of all? And if they do show up, and it's a big if, chances are it's going to be some kind of a scientific mission like what we would do, and they will be just super curious, asking a lot of questions. There's really no point of suggesting that they would be hostile. It's not a hostile species would probably not be traveling across the universe destroying everything. It just doesn't really make a lot of sense. Oh, here we go. One and okay, I hope there's sound. Oh, the galaxy, the Milky Way. I'm hoping. Oh, here we go. Okay, that was a little bit too loud. Okay, I'm gonna. While we're watching this, someone was asking me about James Webb Telescope. How far? So this is from Giles Caldersmith. How far do I think it will be seen? And if it's going to bridge the gap between different models of physics. To be honest, in terms of distance, it's going to be really, really far. Like oh, okay. I'll come back to this in a second.
At the European Southern Observatory, or ESO for short. Thank you to everyone watching us online as well. Today, we'll be hearing from the Event Horizon Telescope collaboration about their newest results, so please do switch off your mobile phones to hear them. I'm Barbara Freire, I'm the media manager at ESO, and since we don't have much time until the main results go live in multiple press conferences around the world, I'll quickly present the format of today's event. First, we will hear from ESO's Director General, Xavier Barcons, and then from lead Event Horizon collaboration scientists about the main research. We'll then open the floor for questions from journalists only, be it those here in the room or those watching remotely. I will now hand over to Xavier to open the proceedings.
Okay, so I'm going to be here in the background, so if you have questions, ask.
Thank you. Good afternoon warm welcome to ESO to everyone. It's really great pleasure to be here today, hosting the members of the Event Horizon Telescope collaboration as they prepare to announce their most anticipated results following the unveiling of the first image of a black hole back in 2019. Today, we're going to see something really new, exciting, extraordinary at the center of our galaxy for the first time. We've been so close to it many times before. ESO facilities like the Very Large Telescope and the VLT interferometer, in addition to the Keck telescopes in the US, have observed stars moving around the compact invisible object at the heart of the Milky Way. And for sure, the ESO Extremely Large Telescope will continue doing this in the future towards the end of the decade. The movements of these stars have been tracked for decades using specially crafted instrumentations. These measurements offer the best and very solid evidence so far that these stars can only be orbiting a supermassive black hole. Reinhard Genzel, who is with us today, thank you very much for joining us, was awarded the Nobel Prize back in 2020 together with Andrea Ghez in the US for exactly this discovery. But we are yet to see direct visual evidence of this compact object, which astronomers call Sagittarius A star. This extraordinary result would not have been possible to achieve by one single facility or even by the national astronomical community of a single country. It took 8 radio observatories around the world, and that network has already expanded to 11 today. Many built, funded, operated, and supported through international organizations across many countries around the world. Among those, ALMA and APEX in the Atacama Desert of Chile, which are co-owned and co-operated by ESO, as well as European facility like the IRAM 30-meter telescope in Pico Veleta and the NOEMA array in the French Alps. It also involved an international team of about 300 scientists, plus many others supporting them, like engineers and many more people. And altogether, it shows what we can achieve when we cooperate, when we work together. This is very important to remember in the times that we are living in, where the world is not running in that direction, unfortunately. ESO was founded 60 years ago, precisely to foster international cooperation in astronomy, so we can jointly tackle the biggest open questions in the universe. And indeed, a key motivation for ESO to put its telescopes in the Southern Hemisphere was to enable science to be done around the center of the Milky Way. So this is why it's such a big pleasure today to be here hosting this event. Together with me, I have 2 of the leading figures of the collaboration, the EHT project director, Joop van Lankevelde, chief scientist at JIVE and also professor at Leiden University, and the founding chair of the EHT board, Anton, director of the Max Planck Institute for Radio Astronomy in Bonn. Anton will later be telling us about the European facilities involved in the EHT, and now Joop will now present the main result. So over to you, Joop. Thank you very much.
Thank you, Javier. When I entered the field of radio astronomy as a student, I was told about this enigma, this mysterious radio source, Sgr A star, at the heart of our galaxy. I observed it at long wavelengths, and there it appears to be blurred. It's very exciting here today to show you today this best ever image of that enigma, Sgr A star. I will do that with my team, or with the team, but I would first like to remind you that the team is much bigger than fits in this audience. In fact, it's bigger than fits in the auditoria around the world where this press event is taking place simultaneously. We are over 300 people on these papers, and only very few of us get to be staged here today to share the result with you. To share the result, we will be flying into the heart of the galaxy, some 27,000 light years away from us, We will do that in 45 seconds. That's a violation of Einstein right away, but maybe that's probably the only violation of Einstein. So we start out from the plains of Chile, where the ALMA telescope is located, and we're going to zoom in to Sagittarius, the Archer, which is high in the sky above the, northern Chile. And we will go and zoom in first in the optical, but we have to switch to the infrared because there we can penetrate all the way into the galaxy. We leave tens of millions of stars behind, and we get to the place where stars are in orbit around a dark spot. And when we switch then to our radio eyes and we use a network of telescopes to resolve further and further, I can present to you the image of Sgr star, the black hole at the galactic center.
That is awesome! I almost forgot to turn on myself for a second. That is insane. Okay,
I will now introduce my team.
Oops,
This is the first image of the supermassive black hole at the heart of our Milky Way galaxy, Sagittarius A star. For decades, we have known about a compact object that is at the heart of our galaxy that is 4 million times more massive than our sun. Today, right this moment, we have direct evidence that this object is a black hole. The black hole resides inside the dark region at the center of this image, where its gravitational pull is so strong that light cannot escape and only darkness remains. We call this region the shadow of the black hole. This region is surrounded by very hot gas swirling around the black hole. This gas emits radio waves we observe with the Event Horizon Telescope. These radio waves create the glow we observe around the shadow of the black hole. From our image, we measure the size of the shadow of Sagittarius A star to be 52 micro-arcseconds on the sky. This is about the size of a donut on the surface of the moon as seen from Earth. In reality, Sagittarius A star is about as big as the orbit of Mercury around the sun, but at a distance of 27,000 light years. Because the size of a black hole shadow is proportional to its mass, our image tells us that the mass of Sagittarius A star is 4 million times greater than that of our sun. It is really incredible that this prediction from Einstein's theory of general relativity matches the mass measured by the Nobel Prize-winning studies of stellar orbits in our galactic center. Today's image might look familiar to some of you. We were all amazed that the image of Sagittarius A star looked so similar to that of the famous black hole in the M87 galaxy, an image our team revealed back in 2019. However, Sagittarius A star is over 1,000 times less massive than M87 star. If Sagittarius A star were the size of this donut right here, tiny, M87 star would be the size of the Allianz Arena, the Munich football stadium just a few kilometers from where we are today. On top of that, Sagittarius A star consumes gas at a much slower rate than M87 star. And these two black holes also reside in completely different environments. Sagittarius A star resides at the center of our small spiral galaxy, whereas M87 star resides at the center of a giant elliptical galaxy and ejects a powerful jet of plasma. Despite all these differences, the images of these two black holes look very similar. Why is that? This similarity reveals to us a key aspect of black holes. No matter their size or the environment they live in, once you arrive at the edge of a black hole, gravity takes over. The journey to the edge of Sagittarius A star spanned decades of technical and scientific developments, and I will pass it on to my colleague Thomas to tell you all about our adventure. Thank you very much.
Thank you, Sarah. Imaging a distant black hole would not have been possible without a big telescope of very high magnifying power, or angular resolution, as we astronomers call it. To achieve this, astronomers combined radio telescopes located around the globe to create a super telescope which has the size of the Earth. This technique is called Very Long Baseline Interferometry, or short VLBI. While the Earth is rotating, all telescopes observe the same astronomical objects for several hours. At each telescope, the data are recorded on hard disks and are accurately time-tagged by precise atomic clocks. After observations, the data are shipped to processing centers where they are combined in supercomputers. These supercomputers are called correlators. After a number of quite complex data analysis steps, this results in the high-resolution image of the radio source. It took more than 25 years to optimize this observing technique and make it work also in the short wavelengths 1 millimeter band, where the angular resolution is highest. It required the development of quite complex and very technically challenging techniques and data acquisitions so that the wider observing bandwidth could be used to achieve this better sensitivity. This sensitivity is really needed for the accurate imaging of the faint event horizon scale structures which we are now seeing in Sagittarius A star. A decade of pilot studies paved the way in Europe and in the US for the formation of the Event Horizon Telescope. The EHT is a VLBI network of telescopes which combines radio waves at 1.3 millimeter wavelengths. This wavelength is short enough to see the swirling matter around the black hole. During the Sagittarius observations in 2017, the EHT combined 8 telescopes. Since then, the network has already grown to 11 nowadays. The radio telescopes of the EHT are located at particularly high sites to minimize the influence of the atmosphere and the water vapor on the observations. Examples are the ALMA and APEX telescope in the dry Atacama Desert in Chile, the IRAM 30-meter telescope in the Sierra Nevada close to Granada in Spain, and the NUEMA interferometer in the French Alps. With this, the EHT achieves an angular resolution which is sufficient for the imaging of such distant black holes, and also sufficient for the matter surrounding these black holes. To give you an idea, the EHT can see 3 million times sharper than the human eye. So when you are sitting in a Munich beer garden, for example, one could see the bubbles in a glass of beer in New York. Sagittarius A star was observed by the EHT in 5 observing runs during April 5 to 11 in 2017. These telescopes also included, for example, special places like the South Pole. The telescopes recorded a total of 6,000 terabytes of data, which were then shipped to the 2 correlator centers, one being in Max Planck Institute for Radio Astronomy in Bonn, and the other one at MIT Haystack in Massachusetts, close to Boston in the US. The amount of processed data is really very, very huge. it would basically, if you would print this data on A4 paper, the paper stack would reach the moon. Of course, we are not going to waste such much paper. After correlation, the calibration and sophisticated data analysis took several years and required the development of many, many new tools by the members of the EHT collaboration. In this development, we also honor the substantial contribution of very many young scientists who just start their careers now. For the details of this amazing imaging process, I would like to refer to my colleague and the next speaker, José Luis.
Thank you, Thomas. Thank you very much. Yes, as my colleague Thomas mentioned, the EHT is like a giant Earth-sized telescope, but it doesn't work like a regular telescope. Instead, the radio telescopes of the EHT work in pairs, with each pair collecting the information required to obtain an image. As the Earth rotates, the separation and orientation between telescopes changes, providing this extra data that we need. With the 8 radio telescopes of the EHT, we have enough information to obtain an image, making the EHT the only existing instrument humanity has to image supermassive black holes. Imaging Sgr A was, however, significantly more challenging than M87. Oh my God. It was really a lot harder. Our line of sight to the galactic center is obscured by matter, which scatters radio waves coming from the region around the black hole. But most importantly, as shown in these computer animations, the gas in these 2 black holes moves at the same speed, nearly as fast as the speed of light. But Sgr A star is over 1,000 times smaller than M87. This means that the time that the gas takes to orbit Sgr A is only just a few minutes, while it takes days to weeks to orbit the larger M87. This means that the gas around Sgr A was actually changing while we were observing it. It was like trying to take a clear picture of a running child at night. So you would imagine how difficult and how crazy it drove us for many years. So we EHT scientists have developed sophisticated new tools to account for this rapid movement of gas around Sgr A star. Tens of millions of images of synthetic data created to best resemble that of Sgr A star have been produced in supercomputers around the world to refine all algorithms, like searching for the best lens and filter to get the sharpest ever image in your camera. The EHT collaboration has produced thousands of images of Sgr A star using classical methods and EHT tailored new algorithms for imaging interferometric data. As shown in these images, each one of these images is slightly different, but by averaging these images together, we are able to emphasize the common features, finally revealing the giant larkin at the center of our galaxy for the first time. But it is important to note that not all images look alike. We found that we can cluster these images into 4 different categories. The vast majority of them are contained in 3 clusters with only ring images that only has some changes in the brightness distribution around the ring, and only just a minor cluster with images that doesn't look quite like ring images. Through literally years of exhaustive tests, we are now confident to have captured the first image of the black hole in our galactic center. Sgr A star now holds the record previously set by M87 of the most thoroughly vetted interferometric image that has ever been made. Our detailed analysis of the images, as well as exhaustive modeling of the interferometric data, has revealed that all share exactly the same ring size, precisely measured to be 52 microarcseconds, in perfect agreement with the size predicted by prior observations and theory. Of course, we are thrilled today to show the first image of the black hole in our galactic center. This, together with the previously release of an M87 image, fulfills the initial visionary goal of the EHT. But this actually only marks the beginning of an amazing area in the study of black holes. The ongoing expansion of the EHT and the significant technological upgrades will allow scientists of the EHT to release even more amazing images and, of course, movies of black holes in the future. And now, to learn what this image tells us about the black hole itself, I pass it on to my colleague, Christian. Thank you.
Thank you, Jose. To interpret the image and to learn more about black holes, we performed detailed models how the gas and the light behaves in the direct vicinity of black holes. Our models have 4 ingredients: the black hole, magnetic fields, gas circulating the black hole, and the light emitted by the gas, which is finally collected by the telescopes of the EHT. Astrophysical black holes can be fully described by their mass and their rotation. Black holes can spin either in the same direction as the gas or in the opposite direction. For the model or for the image and the source in the galactic center, we know the mass estimate very good from stars orbiting it. However, the spin of the black hole in the galactic center is rather unknown. In our models, we let mass and matter fall towards the black hole, and this matter forms a disk around it. The gas in the disk is circulating the black hole and heats up. While the gas is heating up, it starts glowing. So thus, in the EHT image, we see the glow of the infalling and outfalling material. Similar to the black hole spin, we don't know exactly what is the orientation of the black hole towards the Earth. And changes in the orientation lead to different image structure and different positions of the bright spot around the ring. Therefore, our modeling needs to cover a large range of possible spins and inclinations. Therefore, we built the largest and most detailed image library for black holes ever. For this purpose, we use supercomputers around the globe, spending billions of CPU hours creating petabytes of data. Finally, we have obtained millions of black hole images, and we compared them not only to the EHT data, but also to historical and complementary data. Our best bet model, which is playing now, shows a lot of fine details. You can see these fine arcs going around the black hole. However, when we consider the resolution of the Event Horizon Telescope, as my colleagues explained, these fine features are blurred out. And you will see this soon. This will switch on to the blurred image. So now you see the transition to the blurring. Now the fine features are gone. This is the resolution of the Event Horizon Telescope. What we found is that the black hole in the galactic center is rotating, and it's seen face on. The implications of our modeling with respect to theory of gravities will be explained by my colleague, Maria Felicia. Thank you.
Thank you, Christian. As our nearest supermassive black hole, Sgr star can be studied in ways that are not possible for other sources, making it a unique laboratory for exploring the astrophysics of black hole and testing prediction of Einstein general relativity. We relaxed the assumption that Sgr star supermassive black hole is described by Einstein theory and quantify possible deviation. Our finding from this new measurement of Sgr star provide further evidence that astrophysical supermassive black holes, independent of their mass, are described by solution of Einstein theory. For such a star, as we found for M87, the infrared size of the black hole shadow is consistent with the prediction of general relativity within the 10%. This consistency is in spite of the fact that Sgr A and M87 are feeding on matter at dramatically different rates, with Sgr A accreting 1 million times less matter. So our conclusion indicates that Einstein theory is still holding strong. And in addition of what was observed for M87, now we have the most compelling evidence to date that the supermassive compact object at the center of our galaxy is a black hole, and that it is in all likelihood described by Einstein theory. We know black hole, and in particular the vicinity of the event horizon, are becoming an observational test bed for gravitational physics. This environment offers us the unique opportunity to determine where and how Einstein theory breaks down. And if it does, of course, will transform our understanding of gravity and the property of space and time. We know very well that the idea of testing Einstein theory using our galactic center black hole is not new. But the result we have shared today represent an important step forward. So I'm delighted to be able to say that we have finally imaged the supermassive black hole at the heart of our galaxy. These measurements have opened a new window onto studying black holes and their role, their central role in our universe. The years ahead, of course, will transform our understanding of a black hole and the fundamental nature of gravity. So stay tuned, because the best is yet to come. Now, I will hand over to my colleague Anton, who will give the closing remark. Thank you.
Good afternoon. This is it. This is it is a huge moment for everyone in the Event Horizon Telescope collaboration. It's the next level. And I'm proud of everyone, of our entire worldwide team. They have worked so hard for this latest breakthrough. You are the first to see our image of the black hole in the center of our galaxy, as close as it gets. Imagine this. We have combined the world's greatest radio telescopes into one Earth-sized camera. To be honest, after doing this for 40 years, I'm still astonished each time we pull this off. Let's shine a spotlight on the European facilities within the EHT, and we begin with the ALMA Observatory. The Atacama Large Millimeter Array at 5,000 meters altitude in the Chilean desert. This was our game changer. Its sensitivity, because of its huge collecting area, was the difference in measuring the weakest signals. And the 30-meter antenna in Spain of IRAM, this has been our flagship for over 2 decades. It is essential for making the sharpest image. The APEX, the Atacama Pathfinder experiment in Chile, near ALMA, is invaluable for precisely calibrating our signals. And the NOEMA, the Northern Extended Millimeter Array in the French Alps, with this huge collecting area and super sensitive receivers, has given a further boost to the EHT. And a supercomputer, our correlator, is a hub for the processing of the enormous data sets that are required to then extract our images. These facilities, which include the 3 largest antennas within the EHT, and the support from our funders, and yes, that's us, the taxpayers, are a sustainable foundation for the continued success of the EHT. and we acknowledge the support of the national funding agencies, of the European Research Council, and of the Commission. Now that said, in its DNA and by our design, the EHT is a truly global enterprise. Well over 300 scientists from over 20 countries, and add to that telescope designers, builders, engineers, technicians, and staff. Their contributions are what the scientific collaboration depends on. In 2019, a little over a century after Albert Einstein revealed his theory of relativity, and after decades of pioneering preparatory work, we presented the first image of a supermassive black hole in the center of the galaxy M87. Nobel Prize-winning measurements by Andrea Ghez and Reinhard Genzel, and we're so happy, Reinhard, that you're with us. With their teams, they showed that there must be such a black hole in our galaxy, and we made this black hole visible for the first time, and it confirms their conclusions. So what about Einstein? Would he smile seeing all this, hundreds of scientists still not having proven him wrong? I rather think that he would be ecstatic, seeing all the experimental possibilities we have in this field today. So, mission accomplished? Yes, but there's so much more to do. We now want to go on and make movies. We want to study magnetic fields. We want to look at the jets in galaxies. And yes, we want to tackle gravitation theory again. New antennas in the EHT, like NOEMA and the African Millimeter Telescope, and ever-improving technology will enable us to do that and much more. So today we're celebrating the first image of the supermassive black hole in our galaxy. And we're talking about what it tells us and why that matters. And tomorrow we'll be back at work unraveling the mysteries of black holes in the universe. Thank you all for being with us today, and now over to your questions.
Thank you to our speakers for sharing this remarkable result with us. Before I open the floor for questions from journalists, I'd like to remind everyone that we have extensive press material, including images and videos, on ESO.org. For those of you watching online, please stay tuned, because at 4:30 we have a Q&A panel where members of the public will be able to ask questions to EHT experts. But on to questions from the media. If you are a journalist here in the room, please raise your hand. Take your mask when asking a question and speak very closely to the microphone, otherwise we cannot hear you properly on the stream. Do identify yourself, whom you are reporting for, and whom the question is for. And then we will answer questions from members of the media watching remotely, who have sent in plenty of questions already, a little later. So do we have any questions in the room from journalists or media participants? All right, if not, we can start. Oh, okay.
Hi, so I'm Teresa Paneke. I'm actually a PhD student here at ESO, and I do science communication online through social media. So thank you very much for this amazing result. I would like to ask, because we've talked a lot, or it's been said a lot, that M87 has an active black hole, whereas our black hole is maybe not accreting as much material. So when we just look at the image, they seem to be equally bright. Of course, there's the distance difference, but what exactly is the material we're seeing there? Do we have an idea about accretion rates? So what is the difference between M87 and Sgr A in that regard?
So as you already heard, the difference is the central mass already. So the galactic center has roughly a mass of 4 million solar masses, as Professor Genzel showed us already, and M87 has billions of solar masses. The other difference that you may have noticed on my animations or from images of M87 is a powerful jet that is generated in M87. For the galactic center, we see it, as I showed you, phase on. So the jet, if it's existing, is pointing towards us. It's very dilute, so we can't, at the moment, image it, and I would refer then to my colleagues to explain you a bit what we need to finally detect it. And I think these are the three major differences. It's the mass, it's the jet that's existing, and as already you said, it's a different mass accretion rate, which we have for both systems. So maybe one of my colleagues.
Yes, thank you very much, Christian. Yes. In order to obtain the image, we need to have measurements of with antennas at different separations to measure features that are very small and features that are very large. So in order to capture a possible jet inside a star and to actually capture the jet that we do know exists in M87, we need to have measurements of telescopes with short separation to see these larger scales. We lacked that information during 2017 observations, and this is why we did not see the jet in the M87, and we have not seen any jet inside J star. We do have new antennas in the observations that followed the 2017 campaign, and we do expect to see the jet in M87. It is still unclear how bright, if there is a jet inside J star, but we will be chasing it, of course.
Thank you. Yes?
Hi, thank you so much. This was very exciting for me. My name is Camila. I am with the Brazilian podcast Astronomy em Meia Hora. And I wanted to ask if the collaboration has other targets in mind already, anything like planned to observe in the future.
Well, thanks for the question. Yes, of course, we have other targets in mind. I mean, during these observing runs, we not only observed M87 Sagittarius, a star, but we observed also a number of AGN, some of which are very close by. And data analysis of this is still ongoing, but give you a warning, since they are so distant, we will be not able to see these beautiful shadow-like images immediately. So it would require more sensitivity to really look at the very closest objects, and we are at the moment surveying the sky to find these.
Thank you. I'll take questions online now because the list is piling up. So this one is from Hans Heckenberg from New Scientist Dutch edition, and it's addressed to Sarah. What open questions that we currently have about the structure of black holes can be answered by this image and follow-up images of Sag star?
Ooh, that's a loaded question. Yes, so open questions that we can answer. I think Kristen's portion of the presentation summarized really well the major things we found out about Sag star, which is one of the unknowns is the black hole spinning, which we have the answer to that. Yes, it is. And what is the orientation of the black hole with respect to us, which we also did not know before. And now we're fairly confident that it is pointed more or less towards us, so face on. These properties, this knowledge of the fundamental properties of the black hole will help us study the astrophysics of the black hole in more detail later on, and also how we interpret the images. The spin and inclination have very important roles in how the image looks and how we interpret the astrophysics we can learn from it. Future observations of Sag star, of course, our current observations from 2017 also have polarization information, which we are planning to start working on, like Anton said, tomorrow. That will tell us information about magnetic fields around the black hole. And magnetic fields can tell us about how the black hole eats gas and ejects possibly a jet or outflow. So as Christian said, we still don't know if Sag star has a jet. Some of the models seem to hint towards that direction, but magnetic fields, learning their configuration, how they look around the ring of Sag star, will help us answer these questions very soon.
Thank you. Okay, I'll continue with the online questions. So we have from David Castelvecchi reporting for Nature. This is addressed to any of you. How does the measured angular size compare with the mass of 4.15 million solar masses measured by Genzel's group? Would like to take that one? Maria Felice?
It was very important to have their measurement, their astrometric measurement to us, because what we found that the size of our ring of the shadow is consistent with that mass. As Sarah said before, no, that the size is proportional to the mass and to the distance. For us was important this, and
okay, thank you. All right, we'll continue with the online questions. So from Sanja Venkart, reporting for Wolfgang magazine in Vienna, also addressed to any of you. What are the difficulties when observing and analyzing Sagittarius A star? Maybe more for José.
Very happy to answer this. Well, many. I mean, oh my God, where do I start? I mean, the most difficult part of Sag is that it's a very small black hole as compared with M87, 1,000 times smaller than this. And then we had to try to find a way in which we can overcome these extreme changes in the emission that we were observing, as we were explaining before. In order to capture an image of the black hole, we need to take a very long exposure snapshot. We are observing these sources for 8 to 10 hours. And the basic principle of the technique that we are using is that during those 10 to 8 hours, your object is not changing. And this is exactly what refuses to do Sag A star. So in order to that, we have created these new tools that allow us to get a little bit blurry image, adding a little bit of extra noise to compensate this variability, so that even though the image may be a little bit blurred than the image that we got from M87, we do capture the main features, the most salient nature of the black hole. And this is the ring structure and all these images that we were showing before. They all share the same ring size. What we were not able to capture is what is, the brightest emission around the ring. And this is because it's changing. So we are getting these different images, all consistent with a ring, 52 microseconds, but the emission around the ring changes when we make slight changes in the way we make the images. Like we change a little bit the lens, or we change a little bit the filter, and then the image looks a little bit different. But the main image is there. And all this analysis is what took us more than 2 years, from 300 people in the collaboration, from doing the imaging, from doing the analysis, and etc.
Thank you. Okay, I don't see any hands up here, so I'll continue with the online questions. We have one from Filip Ogorzelski from TVP Nauka. This is addressed to any of you again. How much matter is being absorbed by the black hole in the center of the Milky Way? Christian?
I'm not exactly sure what he means by absorbed, but the accretion rate. Yeah. So actually, these black holes in the galactic center is secreting very, very less matter. They are basically, this black hole is basically starving. The accretion rate is extremely low, and yeah, the accretion rate is extremely low. Maybe Sarah.
Thank you for that. We calculated this for a fun EHT Twitter poll that we had. So if you were to have the same diet as Sagittarius A star scaled to your mass, you would eat 1 grain of rice every 1,000,000 years.
I would not want that diet.
No.
All right. We have a question from Antonio Pires, reporting for astronomia.com. How much did the telescopes that recently joined the HT collaboration improve the results from the previous observations in terms of resolution and sensitivity? Will we be able to increase the apparent aperture by using space telescopes in the foreseeable future? This be perhaps for Thomas?
Well, first, of course, this image which we created now has the same configuration. So the 2017 data of M87 and Sagittarius A star based on the same telescope configuration. In 2018 and following observations, we have added more telescopes. Now we have 11 telescopes, so we fill the UV plane much better. That means we can much better make a synthetic telescope, and the participation of NOEMA and also of KitPeak, for example, provided additional baseline sensitivity. We also expanded the recording rates and doubled the observing bandwidths. So all this lets us hope that in 2022, where we just observed the source again a couple of weeks ago, we will get a much better image.
Thank you. Okay, we have one from Dave Adalian, reporting for earthsky.org. And I think Christian would probably be able to answer that one. When the orientation of Sagittarius A star is said to be face on, does that mean one of the black hole poles is directed towards Earth? Do we know how fast Sagittarius A star processes, and what is the nature of the particles ejected?
Okay, so let me start first. So we found that it's face on, so this is correct, that one of the spin axes is pointing more or less towards us. The other part was about the material or the emission actually that we see. And what we model is synchrotron radiation. So you have particles, mainly electrons, gyrating magnetic fields, and while they gyrate the magnetic fields, they emit emission, and this emission is synchrotron. And this is what we actually see. And there was a third part. Could you please repeat this?
So it was the processes.
Yes. So precession, I think what you mean is spin. So what we have actually is we have some kind of best bet models. So we have not found an exact model which could explain everything. So we have best bet models and best bet regions. And there we could say that it's spinning, and it's spinning in the same direction as the gas orbiting it, but the precise number of the spin has to be obtained in upcoming observations.
Thank you. Okay, we continue with the online questions. We have one from Roberto Peixoto, reporting for Geo Globo in Brazil. EHT observatories capture radio waves, but how do black holes emit these waves, and how can we build an image with it? Who wants to take this one?
Emission, how it produced is I already explained. That's the synchrotron radiation. So basically you accrete gas, which is electrons, they gyrate, produce the emission. And for the details of how we actually detect this and so on, I would refer to one of my colleagues working on data processing and imaging.
Is that for José, Thomas?
Yes. Then the most important part, of course, is to get an image. As we were explaining before, the EHT doesn't work like a regular telescope, so we cannot build a telescope the size of the Earth, obviously. We cannot do this. But what we do is we have these different telescopes that act like segments of this huge telescope. And then we collect the signal from all of them and synthesize the virtual telescope on a computer. Once we do this, and then it is possible to have basically like the Earth-size telescope and get an image like you would get an image with your mobile phone. But it is significantly more complex. You have to do. You have to make the images on supercomputers, so it's a process which is extremely complicated. But at the end, you are able to finally obtain the images of these supermassive black holes.
Okay, thank you. Another question online is from Doris Urrutia, reporting for Inverse. How did you feel when you saw this new result? What was the big reason that you felt excited enough with your finding to share it with the world? Who wants to take this one? Sarah?
So I did my PhD research on Sagittarius A star, trying to chase down this jet that is maybe real, maybe a myth. And so I was working on images of Sag A star at a lower frequency than EHT, so images that aren't quite a high enough frequency to be able to peer through all the gas and see the shadow. And I was trying to understand where this radio emission comes from near Sag A star, try to see if we could constrain the inclination of the black hole from my observations. And until today, I was also the record holder for the best image of Sgr A star. So when working on EHT, I saw the image of the shadow. It was a really special moment because I've been working on this source for a long time through my PhD and trying to understand its properties. And there it was, staring back at me. And I felt, shivers and excitement. And, it was revealed as part of the whole imaging teams coming together, just like for M87. We're all on a Zoom call. I was in Japan with a few people at a Galactic Center conference, which was quite funny. It was midnight, Japan time, when we had the telecon, and we all huddled together, and the images, like Jose was leading the telecon, images were revealed from all the different teams, and everybody saw this ring of the same size. And it was such an exciting day and very memorable to finally see this object I've been working on for a long time.
How? Did you want to add?
I wanted to say one thing to Sarah. She's still the record holder.
Yeah, but now I have to share it.
Did you want to add something as well, Thomas?
Of course, this is all correct, but as a little bit older person, I realized how it all started. And I think it took now more than 30 years to get the image. So we had this idea long ago, and at that time when we started observing, the first experiments at 1 millimeter failed horribly, and we have to step back to 2 millimeter before we could do it at 1 millimeter again. And I saw that over the years, the techniques have improved so much. That's really a very, very good feeling to see now that it has worked and that we are now finally able to show that image.
That's great. I'm also very glad that you are able to share it. Okay, one more question online. It comes from Diego Garcia, reporting for Canal Sur TV. This is addressed to Jose because he wants you to answer in Spanish, but someone else could answer in English as well, I suppose. During this process, what have you discovered at a scientific level about Sagittarius A star that was not known before? And then there's a second part to that question. What are the biggest differences between this image and the one of the black hole in M87?
Okay, thank you very much, Diego. I probably should answer this in English for the whole community. Thanks again for your question. Yes, I think the most important thing we have learned is that first we have the visual confirmation of the black hole that was predicted a long time ago. As my colleague Christian mentioned and Maria Felicia, now we have a constraint about how fast this black hole rotates. And this is very important because we think that the rotation of the black holes provides the energy that powers this huge jet that we see like in M87. And the second part of the question was probably...
So there was one about the differences, and
yeah.
My colleagues moved the question already. So
all right, okay, it's fine.
If they can fetch it.
Sure, no, it's fine.
Okay.
Fine. Sorry, I forgot.
It's important also because for the second time, we were so close to the event horizon, and then we were able to test gravity at a different regime, at different scale. And we were surprised also that general relativity is still holding. It's incredible.
So I have the question back, and it was two parts. What have you discovered about Sagittarius A star that was known before, and the differences between the images between M87?
Yes. Well, the images are surprisingly similar. I mean, as we were discussing, these two black holes they both live in completely different environments. Yet, at the end, the image is just mainly made out of the gravitational pull, as Sarah was mentioning. So, in that sense, this confirms one of the most important predictions from general relativity, which is that these are the most amazing, extravagant objects in the universe, yet the simplest. They are just as simple as a a sphere or a circle in images.
Thomas?
Well, also with regard to the published results from gravity, I think there's a major difference. M87 is far away and it's much bigger, so it varies much slower. But in Sagittarius A star, we really can see the variations. I mean, we see basically bright features moving around. Although we are not able really to trace their motion exactly, We have published in our papers some models which explain this motion already, and I think the next step would be to parameterize the motion so that one can do more science out of it.
Thank you. Okay, I will continue with the online questions. We have one from Alejandra Lopez reporting for El Tiempo in Colombia. This is to any of you. So she asks, perhaps Christian, what is the orientation of the rotation of this black hole with respect to the plane of the galaxy? Do we have an answer to that?
So what I mentioned is we see it face on, and according to our models and this bad region, the rotation is in the same direction as the gas. And please, all my colleagues, correct me. It's in a counterclockwise way when you look on it. When you look at the images, it's turning counterclockwise. At least in the simulation. So the simulations, you see that it's turning in a counterclockwise way.
Okay. We have time for one more question. I'll give priority to journalists here in the room. If not, I'll continue with the online questions. And we have one from Tushnet Physics World. Do we have any ideas on why there is such mass difference between Sagittarius A star and M87 when they are both supermassive black holes? Who wants to take this one? How?
Okay. Am I on? So that's most likely to do with the evolution of the galaxies in which they are found. M87 is a very giant elliptical galaxy, and it's probably the result of merging many galaxies with many black holes together, while our galaxy has been going through much less evolution.
Okay, thank you. All right, I will stop now because we are almost at the hour, and I will thank our speakers again, and thank you all for the questions, also for those watching remotely. Journalists are now welcome to approach our panelists and other experts in the room. So EHT experts have a badge with an orange color in it, and then there are also other experts who are not part of the EHT team but can answer questions about the research, who have a badge with a green color. And we have interview areas available here and up there, and you can approach myself or one of my colleagues to be guided to them. For members of the public watching remotely, do stay tuned because we have a YouTube Q&A coming up at 4:30. And then before that, we will actually have a special musical performance just before this Q&A session. Do go to @ESO on Twitter to find out more about it. Thank you all very much, and thank you. Thank you.
Okay. I guess maybe sort of done. I'm gonna stick around, see if they have anything else announced. There were a lot of questions. I tried to answer some of them. Those of you watching probably may not see most of them.
So welcome everyone once again.
We're
here from the European Southern Observatory in Munich, Germany. Very, very excited about this amazing image we just saw.
Let me actually put her on mute for a second. And I'm going to just read the subtitle, see if she says anything important. Not because I don't want to hear what she says, but because there were a lot of questions that people were asking. And I actually wanted to just answer some of them so that those of you watching this afterwards might be able to hear the answers. So one of the questions was in regards to, let me bring up the image. In regards to the image itself. So this is the image that they just revealed. And it has these unusual 3 dots. Now, this is a preliminary conclusion from what I've heard them say, and I'm going to have to double check this. But, okay, normally, if you were to look at a typical black hole, which I'm going to try to bring up right now, let me just show you the most famous one from the famous French astronomer who, unfortunately, is not as popular as he should be, Jean-Pierre Luminet. He created this iconic image that you're about to see right here. Are you seeing it? Yes, maybe. This image right here was created back in like 1970, I'm going to say 4, 2, 3, 2, I don't know, 70s. And it was made using punch cards. And basically, this is his simulation of what a black hole should technically look like. And notice how right in this area right here, you have this really bright spot. And this is created because, well, you have all of this stuff moving toward you really, really fast. And it creates a lot of sort of energy in this spot. And also, there's obviously a lot of blue shifting going on here. And then this part is sort of moving away from us. So there's this motion that we're observing. And so you expect to have this one spot that's bright and maybe other spots that are dark and not as visible. However, if we were to look at what we have now received from EHT, it looks entirely different, right? It has 3 spots, and it's, I mean, it kind of resembles some sort of like a pancake-like structure. They call it a donut. And it creates questions, right? Like, what's happening here? Well, right now, my guess is, based on what they've announced, is that it's basically a combination. It's a statistical addition of thousands of different simulations they created from the data they received from the telescopes, and it's an averaging process that created this image. So basically, by averaging every image, and certain images would have spot here, certain images might have a brighter spot here if there's something coming from that side, and it sort of creates accretion disk effects that are making it more bright. It's not necessarily due to the motion of the accretion disk itself. It seems to be due to the effects from basically the activity around the black hole. At least that's what I got from the explanation they have so far. I'm going to have to look it up again, and I'm going to have to do some research and present this in the final video that I'm going to be making. But that is kind of what those spots, I think, are. And very unusual, very strange. Not what I expected, to be honest. I really thought it's going to be like the luminous iconic image right here. And instead, we got this. I wanted this. We got this. And not this. Well, I don't know why. Actually, I do know why, because it's really... Oh, yeah, so one more question someone was asking. Why do we see so much blur? What is this, a potato picture? And, people said their Nokia phones used to take better pictures than this. True, very true. However, in their defense, it's really far away. It's like 26,000 light years away from us. And, I mean, it's a size of a little donut on the moon. And you're taking a picture of a donut on the moon by using a telescope. And in this case, it's not even that many telescopes. It's like, 8, I think, around the planet. And so there's a limited amount of data they're getting, and they have to work with that data to create these images. So that kind of hopefully explains some stuff. Let's see if there are any important questions anyone has, anything that was not clear. I'm going to come back to the stuff they're explaining and talking about in a second, but okay, I don't see anything here. Oh, one more thing I was going to show you. So one of the images I think they showed, or at least I wanted them to show, is this. This is super iconic and super important, and I'm going to remove myself. This is one of the most iconic images or videos that took like 2 decades to produce. And this literally shows us, or proved, that there is a black hole in the center. This is the images of stars moving around something invisible in the center of the galaxy. And that is how they realized there's some kind of a maybe black hole there. And eventually, this region became known as Sagittarius A star, with the star being, the anomaly. And so it's not like a star. It's not a star like our sun. It's just a star, an asterisk. And so therefore, that is important. And eventually, as scientists observed more and more, they started to discover more stuff. They started to see motion of different stars, started measuring Einsteinian effects around this region, and realized that, well, it cannot be anything else but a relatively massive black hole that's approximately 4.3 million masses of the sun, which is approximately 1,000 times less massive than the one in the M87 galaxy. That one is like 6 billion, I think, if I remember correctly. Coolio. Okay, let's see if there are any important questions. Anything I missed? Why don't we use space telescopes to take the images? So remember, the telescope they used, let me show you what it sort of resembles. And those of you who are asking those questions really should be watching that video from a few days ago. I've explained all of this. I sound like a grumpy teacher that expects his students to do homework before they come to the stream. I'm kidding. I'm totally going to answer it. All right, so here we go. This is EHT. Okay, here we go. I can't make it smaller. Come on, here we go. This is EHT. How many do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 telescopes. Those are radio telescopes located around the planet. And together, they kind of create this Earth-sized aperture radio telescope, which is basically like, millions, I guess it's millions of times bigger than James Webb telescope in terms of size of the aperture. And that is really incomparable to anything else we have. So this is an Earth-sized telescope taking a picture of something really, really far away. None of the space telescopes can even come close to this. Like this, not even remotely. Like you cannot even possibly see anything there. Any image that Hubble will take will probably, or not Hubble, James Webb will take, will probably look something like this. And maybe they'll have some stars here and there. But even that is going to be pretty challenging. Like it's just going to be impossible. Okay, so recent question. I missed what the scientists said about black hole facing us. Are the poles facing us, or is it oriented differently? $1 million question. So this is why I guess science communication exists, because as a scientist, your job is to do science. It's not really to explain things, and sometimes they don't explain things well. I'm going to have to read their actual report to answer this concretely. At the moment, I'm going to say that their preliminary discovery is that it seems to be pointed toward us, and it seems that the accretion disk is sort of it's sort of around. It's not directly at us. It's not really like, face on, but it's kind of like at an angle toward us. That is not at all what any of us thought or believed, for one very important reason from recent discoveries, which maybe I'll be able to find here. Sagittarius A star, Jets, I guess. What was it called? I forgot what the actual paper was called. This is from just a few months ago too, when the scientists actually. Oh, here we go. Is that the image? Now, if you're the scientist watching this and you're upset that I'm using your image without telling people who you are, I'm really sorry. I usually put all sorts of references in the videos, but not this time. This time I just can't. I'm sorry, I can't. Here we go. Okay. Very recently, there was a discovery that, there's a proposed jet that they observed that's coming from Sagittarius A star, and it seems to be pointed, perpendicular. It seems to be pointed like that, 90 degrees-ish. This was discovered not so long ago. The image is not very good here. And also, this was, this was pretty groundbreaking. And they saw the actual signs of eruption from just a few thousand years ago. Now, so there's one possibility here is that, well, maybe in those few thousand years, the black hole actually, shifted. Not the black hole, but maybe the accretion disk shifted. And maybe now it's sort of in that other direction, slightly toward us. If so, that is, that's crazy. Why? How? I guess there's some kind of a precession going on. Something that I personally don't understand how you could do that, but I'm sure there will be explanations. Or maybe, and this is just a big maybe, someone made a mistake somewhere. Maybe the announcement or the announcer or the answer during the session was incorrect. Maybe we made an assumption based on just misinterpretation. I don't know. To be honest, I really don't know. I'm kind of curious to find out. So yeah. We're gonna find out soon enough. I'm gonna do some research on this. At the moment, it does look like, according to this image, it looks like it's sort of kind of pointed a little bit toward us, but not directly at us, which is cool, which is really, really cool. Cool. Next story, next question. Let's see, what else do we have? Could we use another object as a lens to get a high resolution? So yeah, there are definitely propositions to use other objects as a lens. Like, for example, there was a recent paper from just a few days ago. Someone proposed, it was proposed before by many different people, but using our sun as a kind of a gravitational lensing device, sun as a telescope. And you can maybe then bend the light coming around the sun. And let me see if I can find it. You can bend the light around the sun, and it could allow us to see things like, planets. And that would be really cool, right? Here we go. This is the image I'm looking for. And then once again, image enhanced. Here we go. So, you could technically use our sun as a gravitational lens and put a telescope here and then see planets or see black holes or see other stuff. However, here's the big however. In order for us to make this work, this has to be approximately 160 astronomical units away from the sun. Or no, wait, sorry, I think it's more. I think it's like 600 AU. I think it's 600 AU. Basically, it was supposed to be like 4 times as far away as the Voyager probes are right now. which would take us approximately, using modern technology, 100 years, maybe 150 years to get there. And so in theory, we could do that, but it's just not, at the moment, it's not practical. It's just not something we can do. Next, comment, concern, question. I'm sorry, my voice is slowly dying on me. I'm also in the middle of an allergy season here. I've been sneezing and coughing a lot. So yeah. Is it possible that black hole is just an exotic material and it's the mass imbalance that causes the shifts? Absolutely possible. At the moment, all of the previous predictions about this being exotic material have sort of been disproven based on the observations from other studies that show that 99% this is very likely to be a black hole, nothing else. Simply based on the observations of, that was a cool picture. This observation of how stars, and specifically, wait, what is this? That's not the right paper. Oh, I missed the image. Where did I put it? Here. These stars. So these stars, known as S stars, stars orbiting around the central black hole, their motion can actually tell us exactly what this, whatever in the middle is made from, based on the actual orbital parameters. So if it is exotic material, it's going to actually do certain things differently. And there was a proposition that maybe it was like a type of a dark matter or a type of an exotic material that's just, we're imagining in some of the theories. And turns out that it's not. It's 99% very likely to be a black hole because most of the mass seems to be concentrated in this tiny spot. And the scientists were able to see this through the observations of the star motion. And so unless it's something really weird in the tiny spot, that's not, black hole material, which still would make it a black hole, I guess, because if you put anything in such a tiny space, it would still become a black hole, in theory. Would Jupiter have high enough gravity to use it for lensing? Yes, it would, but it would not be as powerful as the sun, and so it wouldn't really produce as big of a picture. And I'm not sure if anyone has ever done calculations around Jupiter, but people have done calculations about around our planet Earth, and you can, in theory, place a telescope on the moon and then use Earth's, technically the diffraction from the atmosphere. So you know how the light sort of gets diffracted a little bit in the atmosphere, which could then be sort of focused on the moon and collected on the moon, on a near side of the moon by the telescopes placed there, allowing us to see certain objects. But it would only be in that sort of region between the moon and Earth, in that plane of orbit. And so we would be very limited to what we can actually see. Same with Jupiter. You would have to move a lot of things. All right, cool. I need a sip of something. My throat. Cool. All right. So where are we now? Oh, actually, I totally forgot about the stream. What are they up to? Oh, it's finished. Hold on. What does it say? Okay. So I guess they're done. Are they done? Maybe. Well, we're not done yet. I still have some time. I guess it's 11 p.m. here right now, so I have an hour. I'm gonna stay up a little bit late today. I have to wake up early tomorrow because I have to take my son to kindergarten, and he does not go to kindergarten unless Dada comes. That's the life. All right, so next question. Why not design a weaker, cheaper space telescope and send like 10 of them to orbit L2 to have a massive telescope? I mean, those are really great suggestions, and people have thought of them. The answer is really money. Money is really, really the biggest limitation here. The biggest space telescope planned right now that I know of is LISA, and LISA is going to be maybe launched in the next like 14 years, 15 years, 2037. It's going to be, hopefully, if it ever comes to be, it's going to be a space gravitational wave detector. And that's the one that's being actively planned right now. That's going to be the biggest possible space detector we have. Everything else, it's really expensive. I mean, it took, what, $10 billion to launch James Webb Telescope, multiplied by the number of launches, plus, minus, all of the preparation, all of the things you have to work out. So it's hard. It's a lot of money. And, where is that money going to come from? How are you going to justify it? It always comes down to that. Oh, thank you for the donation to the Save the Children, Mr. Anonymous or Mrs. Anonymous or Miss Anonymous, someone anonymous. Awesome. do you think the future, people in the future will laugh at us because we understand the universe wrong? I don't think they will laugh, but just like we sort of think of, people 100 years ago, I mean, we don't laugh at them, right? Like, we don't laugh at the fact that someone was thinking that, for example, in terms of the galaxy being everything, like, sorry, up to about 1920s, everyone believed that we just live in a galaxy, that the universe was just a galaxy. Nobody knew that the universe even existed. Every single galaxy that scientists were observing, and I'm talking about, let me get the image here. Let me get the video at least. I'm talking about these things. Every single galactic object that we've ever seen, people thought these were just different nebula, where planets form, stars form, and so on. And it took years of debates and years of discussions, and people like Hubble, who became iconic after this, to finally prove that, well, those nebula that you see, they're actually, each of them is individual galaxies. And, we know now that scientists were wrong before, and it's not something we're laughing at, but it's something that we learn from, I think. So I don't think everyone's going to be laughing at this. Will they use James Webb to look at this black hole? I don't think so, because first of all, I don't think it's going to be producing a lot of infrared radiation. And in terms of visual observations, it's not going to be that much better than what we already have from other telescopes. So, yeah, I don't think, I mean, they might just for some other studies, but nothing that we would be super interested in. I don't think there's going to be anything coming out of James Webb looking at this that we're going to be learning anything about. It's not going to be that big of a deal. Cool. Why not include space telescopes to make images of Sagittarius A even better? So this was one of the previous propositions, that we could make a space telescope and put it in orbit and increase the aperture of James Webb. That's actually still planned for the future. At the moment, I don't think there are any radio telescopes in operation around any orbits that can actually do that. You needed to have a radio telescope. Remember, these are radio observations. So what you're seeing here, this is radio light. It's not X-rays, it's not gamma rays, it's not anything powerful. These are just radio observations. Or I guess, are there any microwave observations? I could be corrected later on. For now, I'm going to say it's radio, because these are radio telescopes. Okay, next question. Are they going to be pointing James Webb at known spots of gravitational lensing? Well, James Webb is going to be discovering a lot of gravitational lensing, but actually the telescope that I'm super excited about, also video probably coming next week about this, is the, I'm going to mispronounce that, Zhantian, the Chinese Hubble. The one that's going to be orbiting in the same orbit as the Chinese space station, and Tianwen space station. And that one is going to have such an incredible field of view and such an incredible resolution that it's going to be perfect for studying gravitational lensing effects. It's actually one of its main purposes. But we'll talk more about this in that video next week. It is a really, really cool telescope, though, in the sense that it's going to be able to capture approximately 40% of the night skies using same resolution as Hubble. So Hubble by itself only captured I think it's 0.1% of the entire night skies, even though we have these beautiful pictures from Hubble, like the deep field images and so on. It only captured a tiny fraction of everything. But the Chinese Space Telescope, in theory, if it's operational, if everything goes well, in a few years, we'll be able to produce something that's incredibly large in size and in comparison. Mostly because it has the lenses that are approximately 300 times more wide field lenses compared to Hubble. So kudos for that. It's a huge achievement if they can pull it off. Okay, next. And yeah, I'm super excited about James Webb and the first images we see. Did I release the video about this already? I think I did. The James Webb is about to start its first scientific missions. There are 13 missions that it's going to be doing. And the whole point of those missions is to collect data super quick and release it as quick. So we're going to be getting a lot of data in, I guess, a few months, possibly, well, hopefully end of summer. And so there are going to be some really cool pictures. Was Arecibo involved in this project? No, I think Arecibo was not at all, actually. Was it? That's a great question. How do I not know this? Let me check. I don't think it was. I mean, it was already sort of malfunctioning by the time EHT started. And I'm sure someone in the chat knows. No, I guess, yeah, it wasn't involved for sure. So here we have, one more time, let me bring up this picture. All of the telescopes that were participating in this. And the biggest one is ALMA, and the one that is the most difficult to get data from is the one in Antarctica. Apparently, due to the remoteness of this telescope, it takes like months to collect all of the data, because they have to physically bring the hard drives via airplane, and there are not a lot of flights from that region. So every time it collects data, they have to take these hard drives, bring them to, I guess it was MIT this time, I think. Bring it to MIT, where they do all of the analysis, combine all of the data, do the algorithm stuff, and so on. Okay. Cool. What else am I missing? Did you get a new microphone? No, actually, I'm using super old, cheap microphone, because my other microphone doesn't seem to connect well to the setup. Right now, I'm using Windows. Normally, I'm either on Linux or on Mac for recording. And on Windows, I just couldn't figure it out, and I didn't have enough time. The stream was about to start, like an hour before I started preparing, and I totally forgot about the microphone issue that I used to have. So I'm using this really old microphone, and also plus my voice is slowly dying due to allergies and other stuff. Cool. Just appears to be. How likely is it the black hole just appears to be face on, but actually isn't? The likelihood of objects being face on to us is very unlikely, as pointed out with Messi 26. I actually agree with that. I don't think the black hole is face on. I think because of the statistical processing that they use, where they combine thousands of images, maybe through the averaging, it sort of started to appear face on. But I think in reality, what we're actually seeing here, and this is just a guess right now, I still need to confirm this somehow later on. Where's my picture? I think what we're seeing here, oh, I lost my black hole picture again. Anyway, we're looking at a bunch of black hole sides that are averaged to look like this. And I was actually thinking about, what if it's due to the precession of the black hole, which totally would make sense in some sense. Let me maybe use a video here. Let me use a video that I use all the time, my favorite video. So imagine for a second, you're right here, right? This black hole has an accretion disk, and it produces a lot of energy, but most of the energy, if you were to look at it from a single angle, would look like this-ish, right? Where's the Luminez iconic image? Let me just open it up in Google. By the way, M87. You can kind of see the very similar features here. Jean-Pierre Luminez is actually, he's an iconic French astronomer. I'm really shocked that he does not have as much presence online as, for example, other astronomers. Neil deGrasse Tyson, I'm looking at you, because he is just on a completely different level. Oh, I closed it. No. But anyway, what I was trying to say is that he needs more recognition. He has his own blog as well. So this part right here, right? Now, what I think might actually happen here, and this is a big if, and I still need to do some research on it, since we know our black hole is much smaller and less massive than M87, there's a chance that it does actually have a bit of motion, a bit of precession. It moves around, it sort of shifts around a little bit. And we're talking about observations from several years, right? So there's a chance that maybe this part moves around, and maybe it's just we're seeing it from different angles because of the precession, but that's also maybe not what's happening here at all. So I'm just guessing. And I think because of this, the statistical combination of these images created this. So basically, once again, this is not an actual image in a sense that, you know, we're looking at something and we're capturing photons and we're creating this pixel by pixel. That's not what's happening here. The way they collect the data is the data was collected, and then they used the algorithm, knowing what we know about black holes and how they spin, to try to match it with the most likely image they think it might represent. And they created, I think they mentioned like several thousand images, or was it 1 million? And so they created a bunch of them, and they all were slightly different. Not exactly the same, but slightly different. But then they just combined them into one. And when you combine all of them into one, you get this. And so that would have those 3 spots, making it look like a kind of a mixture of a donut and a UFO. So there you have it. Cool. And yeah, and it's still a very impressive image. I mean, just the fact that they are able to use that limited data to create this is still very impressive. And you have to remember, even our cameras in our phones, for example, they do something very similar. Digital cameras, they don't necessarily capture pixels directly. They still use processing. That's why you have computer processors in the cameras. They use processing for certain things, and they do recreate images as they think they might look. But in most cases, they do recreate them quite accurately. In this case, this was a more statistical recreation than anything. Very cool, very cool, very cool. Thank you for the congratulations, and really the congratulations goes to you for being a wonderful person. Okay. This is wrong. Someone said this is wrong. Which part? I mean, it could be wrong. I don't know. I'm just guessing. But this is wrong. Which part? Okay. How do you explain the magnetic waves they found in the image if it's combined from different angles? Magnetic waves? What's a magnetic wave? I mean, those are the radio emissions from the accretion disk, and they did, well, so the different angle part, that's just my take on it. And I'm sure it's maybe not, but we don't know. I mean, I don't know. We'll know soon. I'll have to read they haven't released anything yet, so I'll have to read their reports. It's probably going to be a very long read. They mentioned there's like 600 people working on this, so the actual science stuff is going to be very, very long. But yeah, honestly, just a guess. It's just a guess, and the fact that it's, the precession of a black hole is a phenomenon we know exists, but usually around smaller black holes. So black holes do actually, move around. But for a large black hole like ours, it's not something we can expect. But you never know. Hey, Brazil. I love Brazil too. I visited Brazil when I was like 7, I think. And it was awesome. How do we know it's just one supermassive black hole? Well, it's actually based on the observations from many different papers. It's one of the recent observations was the fact that the stars near this whatever in the middle, they orbit in such a way that it cannot really be anything except for a tiny spot with a lot of mass. May the image tell us, the image may tell us about Sagittarius and its surrounding area. Well, this image, unfortunately, is very limited in what it presents us with. It only has radio frequencies from the accretion disk, so it doesn't really tell us anything about the region around the black hole. But yeah. So I don't think, maybe there is more information we don't have from this report, from the visual report they showed us. But at the moment, there doesn't seem to be anything extra from this. Like, for example, for M87, it took them at least a year longer to create the image that is like this, which has these lines on it. These lines are the, this is created by magnetism around the black hole. And so these are the polarized light coming, the polarized radio light coming from the black hole. And that to scientists showed that this was an extremely magnetic region with tons of different interactions, tons of very, very powerful fields, and also gave hints that it's most likely that the magnetism of this black hole is the main force driving everything, not so much gravity to the in the sense that gravity plays a role, but not as big of a role in creating, for example, the astrophysical jets. This seems to be all magnetism. And so this image was iconic in proving that to some extent. But that took a year to produce. And so we might get more data, but right now we don't really have enough. Would a moon-wide telescope provide a better image? Ignoring if it ignores the atmosphere. Well, in this case, the atmosphere was not a big deal because the radio waves, they actually go through our atmosphere. They don't get interrupted by anything. And so you can still see as clearly from planet Earth as you would on the moon. So in that sense, it would be nice to have another one on the moon, but just having it on the moon would not make it better. Cool story. Next question. Can the gravity of stars around the black hole distort the image of the accretion disk? Not really, not the stars that we have around this black hole. So the stars we're talking about here, these ones, they're not massive enough. If one of them was passing in front of Sagittarius A star, it would actually create the gravitational lensing effect that we could use to study stuff. But none of them are. There are no stars in that region. Okay. Could this be fake images? No, not at all. Too much money went into this, and the people doing this, they have absolutely no reason to fake this because, well, they would have made something better. Let's put it that way. The image they created was the best they could do, and this right here kind of is a pretty clear sign that it's not a fake. And also the previous image from M87, they actually did release the techniques, the methods they used, and it becomes pretty clear how they did it, and so very clear that none of this was fake. It's all real. But it is based on these limited observations by each individual telescope. So I guess to maybe explain this a little bit better, where's my image again? Is it this? No. Is it this? No. Is it this? Yeah. So, okay, so imagine, a typical telescope, right? It has a whole sphere, or not a sphere, an actual circle. Here we only have 13 points, 13 pixels of this really big telescope, right? So it's like having this really big telescope that you bought on Amazon, and yet only 13 points work. And so you're trying so hard to look at this distant object, and you're trying to capture everything, but it's just really difficult, right? It's you have to collect so much data for a year, and you have to use these algorithms to try to create things, simply because there's just not enough pixels on your telescope. And so that's kind of what they're dealing with here. Okay. Cool. Do we need to be scared of jets hitting the Earth? No, not these jets at all. And also, I'm still doubtful that it's actually pointing toward us, mostly because there's really no other evidence. The jets we've detected previously were almost 90 degrees away from planet Earth, perpendicular, so nothing to be scared of. And yeah, I'm actually surprised there are no telescopes in Asia, but that's also because in general, also there are telescopes in China, but the Korean and Japanese telescopes, which usually collaborate with a lot of different organizations, first of all, there are no powerful telescopes in the region. It's kind of difficult to build stuff here. And for countries like Japan and Korea, because of the ubiquity of cell phones and a lot of other radio technology, there are practically no spots here that are radio quiet. You want to have a spot where there's no radio emissions, because otherwise you're going to get a lot of interference. In Korea, there's telecommunication everywhere, in Japan as well, even in China, but China does have a few spots where they were able to build the iconic FAST telescope, the biggest radio telescope we have. So yeah. Oh, thank you, Cameron, for reminding me to keep my head up. I'll try. I'm trying my best. It's been a tough couple of months, but I'm trying my best. Cool. Oh, I think I missed a question. Where was it? Is there any idea if the accretion disk density is wildly variant? That's a great question. Nobody really knows right now, because we have not seen the accretion disk of Milky Way black hole yet. And based on the data from this release, hopefully there will be some ideas. But at the moment, not really. I mean, based on the images from before, right? We barely see anything here. Like literally, it's just a black hole. There's nothing there. There are some emissions, X-rays once in a while, but nothing. There was another video I was going to show you from here somewhere. Maybe, let's see if I can find this. Oh, okay, so here's one image from NASA from a few years ago that I might want to add here. This image shows us that Sagittarius A star once in a while emits flares, and these flares are usually because of the material that comes really close to it. And so it's quite likely, and actually there's a big chance, that what we're seeing here are some of these flares just from different regions. That's another explanation. But yeah, and also one more picture I was going to show you, or video, is of something that happened a few years ago as well. Is this an image? Or oh, that's an image. Oops. I was looking for this. Here we go. That's from like 2017. So there was this relatively large cloud of gas that passed close to the black hole. And this was observed by various telescopes. And there was a huge emission, a huge flare. And it most likely broke the object. It could have been a star, but it could have been something else. And so that was all observed, but obviously this is a recreation using computer simulation. But these emissions were observed, and today there's a strong belief that there are certain objects around the black hole that seem to occasionally turn into these gas clouds, but then recombine into these star-like objects, and they're known as G objects. So there's also something else to think about and ruminate. We still don't understand the region very well. Another casual observer, thank you for subscribing and for becoming a member. And also thank you for the donation, whoever donated anonymously. So someone mentioned they seem to be very confident that Sagittarius A is facing us. Were they mistaken? My guess is that as a scientist, sometimes it's very difficult to communicate on the spot. They're better at writing things by, analyzing them, and they're better at written explanations. And so by being on the spot, they might have, I would say, exaggerate things a little bit. I don't think it's certain yet. I don't think it's confirmed. And I think it's a speculation, as in it seems to be pointed kind of toward us, but it's also maybe based on the recreations from thousands of images. But it's definitely not like face on with a jet right at us, because that just doesn't make sense. Someone's telling me to go to sleep. I still have 20 minutes. And then I'm going to go to bed. Maybe in 25. Could these telescopes be used to visualize Jupiters or super Jupiters with a strong radio emission? In theory, yes. In practice, it would be even more difficult, because these objects move even faster than the material around Sagittarius A star. And so if you have a planet that's moving like, several times per year, for example, you're not going to see much. You're going to see just a blur of radio waves. So it doesn't really explain much. Have I ever considered cooperating with Fraser Cain? I did 4 years ago, I believe. This was my first stream ever. We did a stream together. And I do actually, I talked to him a lot. He's a great guy. Unfortunately for me, it's because of our time zone differences, and also because for me, streaming is sort of still a new thing. And he's a professional streamer. It's still hard, but I definitely want to start streaming more and collaborate with several other science communicators. I mean, Fraser has been doing this for like over 2 decades. He's like the boss of the entire field. And I mean, the guy has an asteroid named after him. You're in a league of your own if you have an asteroid named after you. So there's that. Okay. Any other questions? Okay, so can the magnetic field surrounding the black hole really be so strong that it propels matter away despite its massive gravity? Well, that's kind of what's been suggested in the last few years. Actually, one of the answers did come from AHT, and also this I explained that in that video from a few days ago. Let me find this. I'm gonna find this. Here we go. HT released another image, I think exactly a year ago, from, what was the galaxy called? It wasn't, oh yeah, Centaurus A, our neighbor, right? Am I right? I think so. Let me see. Yeah, for sure. Let me try to zoom in and then do this, and then I do this. Okay, and here we go. Oops, wrong button. Here we go. So that's the Centaurus A galaxy, the largest radio object next to us. If you were to see this in radio light, you would actually see this. I kind of mentioned this in the video where I was surprised myself how big it is, because I actually thought it was a little bit smaller than this. And so if you zoom in really, really close to the center, you'll see that there is an astrophysical jet which looks like a corkscrew. It's not straight. It has these like wavy formations with actual signs of polarity or polarization. Apologies. That is a sign that all of this is very likely caused by extremely powerful magnetic fields, because it's kind of impossible to explain it any other way. And also there are no other explanations for how astrophysical jets can form. So basically by twisting these magnetic lines to the extreme, it creates the conditions where the material around the accretion disk, which kind of looks like this stuff, gets sort of twisted and folded and then sort of flies into both directions. Now, the details are still not clear. As a matter of fact, this is one of the bigger mysteries out there. But that's how most scientists today believe all of this works. So the gravity itself is powerful enough, but not powerful enough to hold the material when it comes to these very powerful magnetic fields. And so eventually the jets are created with the material sometimes moving at super ridiculously fast speeds, very close to the speed of light. And if it's actually pointed a little bit toward us, so kind of like from M87, if you look at M87's jet, it is more or less toward us, not really directly at us, but I think there's like maybe 5 degrees or so. Sort of looks like this. So that is almost directly at us. And because of this, and because of how fast this is moving, if you were to measure speed here by measuring individual particles, it will appear to move at approximately 6 times the speed of light. And there's a really cool explanation in regards to this, because it's a visual illusion kind of. It's not an illusion, but it's a kind of a visual phenomenon that's known to the scientists, referred to as superluminal motion. And there's a video somewhere on the channel about this. I think if you look up faster than light on the channel, you'll find the video. It's basically about how the jets, when they're in a certain angle toward us, they'll create this illusion where things are moving a little bit faster than the speed of light, and sometimes up to 20 times faster. So it's a crazy situation. And okay, thank you so much for congratulating me with 1 million subscribers, although I should be congratulating you guys because you're all wonderful for staying for so long. But also, if you're new and if you haven't seen the picture yet, if you missed the image, here it is. This is the image of the iconic M87 in the middle of our own galaxy. And the image that's going to live in infamy as the coolest image we've released in the last few years. All right. Okay, so cool. Let's see, what else am I missing? Will we be able to see the galaxy, the Andromeda black hole? I mean, in theory, yes. It'll be fun to see it. I don't think it's planned though. I'm not sure what the HT is planning next, because their original plan from 6 years ago, was to produce an image of these 2 black holes. The first one was supposed to be Sagittarius A star. That's what we all thought is going to happen in 2019. Turns out it wasn't, it was M87. And so now we have this one. So now I think maybe they'll start working on something else. They're very secretive about this. I mean, it's kind of smart because it creates so much buzz and hype, but they're very secretive. They don't tell anyone anything. When they send us the email, basically, everyone who subscribes to, for example, European Southern Observatory website gets their notification. Or if you're press, for example, you get emails once in a while, and they're like, hey you, shh, don't tell anyone, but you should come to our stream. It might be something about the black hole that we've been trying to create for a while. So it was very, very secretive, but they kind of gave hints about what it's going to be. So yeah. And cool. So some newcomers are asking about the 3 dots in the image. To be discussed later. The assumption I have right now is that it's basically due to the fact that this was created using thousands of images, and certain images had flares here and there and there and there, and overall it sort of created the appearance of 3 dots. But yeah. People are asking me if I'm okay. I mean, emotionally, but physically, I am in the middle of allergy season right now, so my throat is killing me, my nose is killing me, and so yeah, the voice is not where it should be. I had to use a lot of cough drops to record a video recently, but I'm doing okay. I'm doing okay. Cool. Next question. Next caller. What? I think I missed something. Is Andromeda's black hole visible to us? Great question. It's visible to some extent. There was a recent discovery of some kind of unusual shape around Andromeda, which they finally realized was basically a dust cloud. But it should be just as visible as the one around M87. So in theory, they could make a image. But the thing about Andromeda is that it's also farther away. So when it comes to the sizes of black holes, when looking from planet Earth, the biggest one would be M87 because of its sheer mass and size. The second biggest would be Sagittarius A star. I think it's about half the size if you were to look at it from this distance. And Andromeda, because it's 2.5 million light years away from us, it's not that much more massive than the one in the middle of our own galaxy. So it would only be, I think, maybe about a tenth of a size. I'm just guessing here, but like a tenth of a size. So it would be more difficult to produce the image. So yeah. Is the jet pointed at us? No, probably not. It's unlikely. Very unlikely. Yeah, it's not pointed at us, but they are suggesting that the black hole is sort of facing a little bit toward us. So yeah. Okay. Oh yeah, so yeah, it's true that John mentioned that researchers at the EHT said it would be very difficult for us to see more black holes from Earth. We need more telescopes, and I think that's exactly what they mentioned a few years ago. That at the moment, these are the only two black holes we can, in theory, produce images from, and it would be impossible to do with anything else just because of the distances and the speeds involved around those black holes and just the sheer amount of data they'll have to process. So yeah. Okay. And okay. Have I reached the level of wonderful? I'm not wonderful. I'm saying you're wonderful. Every video I've been saying that you're wonderful, not me. I'm not. I'm still trying. Okay, so a lot of people are obviously unhappy with the picture, the quality. Yeah, it's not your Samsung Galaxy S22 quality. Yeah, it can use some work, but it's far. It's 26,000 light years away. Try to use your smartphone to take a picture of anything that far. So yeah. So it's definitely they'll definitely improve the image once they collect more data. This is the preliminary image that they have. Do I think we can image the collision of black holes? Well, I mean, gravitational waves are doing that all the time, so yes. But in terms of the actual images, there's probably not much to see because the gravitational waves very, very rarely produce anything visual unless there are accretion disks interacting. And in that sense, it has been seen through X-rays, for example. There were several X-rays detected from one of the collisions. But in terms of radio waves, there's not much to see there. I don't think they're going to be visible. And yeah, it's actually really crazy that they use 6,000 terabytes of data to create this. 6,000 terabytes. That's a lot. That's a lot of hard drives. And I definitely agree that this was brilliant work. Someone else mentioned that this is just incredible. Yeah, the quality of the image is not there yet, but remember, this is just the first step. And just like with M87, they're going to be collecting more and more data. They're going to be producing better images, more discoveries coming from this region. How many hours does it go into one video? Well, for regular videos that I make, it takes me about 5 hours, I think. But I spread them across a few days time. So I usually just record everything at once and then just edit everything at once and prepare everything at once. But it does take a lot. Why would we not expect jets to be perpendicular to the galactic plane? I think that is actually exactly what's expected, because that's what's been found by several previous studies. And so I, right now, as a lot of other people are, am very surprised that they mentioned that it seems to be face on. And I'm kind of waiting for an explanation to what's happening here. And yeah, so at the moment, I cannot say with certainty what exactly they mean by this, but the jets definitively have been discovered to be pointed sort of perpendicularly this way. So that's something that came from a recent study. So yeah. Yeah. Okay. Cool. Thank you for all the congratulations and all of the good comments, nice comments, all of the love and support. How big is Sagittarius event horizon? The black hole's event horizon is, oh, I knew that by heart a long time ago. I even made a video about it and I forgot. It's not that big. It's really not that big. I think it's a little bit bigger than our sun. I think in terms of size, it's just a little bit over. I can look it up. Why am I guessing? But yeah, it's just a little bit bigger than our sun, which doesn't make it that big, to be honest. But also that's just the event horizon. On top of that, it also has the black hole's shadow, where basically the light gets stuck and cannot escape, and that's a little bit farther away. But it doesn't go beyond like 1 million kilometers in radius, I think. I don't remember, but not very big, not small, not big. Compared to other galaxies, it's actually on the smaller size. There's a galaxy that was discovered very, very close to us, a dwarf galaxy, a very, very small dwarf galaxy. I think it was called Malin 8? No. The names. I always forget the names. And it's barely even visible. It's very, very dim. But the black hole inside that tiny galaxy was half the mass of our own black hole, which suggests that, well, there are a lot of smaller galaxies that have really huge black holes, which our galaxy does not. So there we go. Hopefully that answers the question. Okay, someone mentioned that volume-wise, it's 17 times the diameter of the sun. Thank you. Hopefully that's correct. Radius is 13.6 million kilometers. That kind of makes sense. Okay. Yeah. So a little bit bigger than the sun. Thank you for the donations for the Save the Children Foundation. All of the money goes to them. I spoke to them recently. They definitely are putting a lot of money into the conflict zones, and specifically in Ukraine and countries like Poland, where they're helping refugees. And it's all going to help the kids. Cool. Thank you for all of the comments. Is there a relationship between a galaxy size and a black hole size? Does a galaxy need a black hole? The answer is no and no. So there does not seem to be a relationship between the galaxy size and the black hole size. Some galaxies seem to have huge ones, some of them have really small ones. And no, some galaxies do not have any black holes. The galaxy that I usually refer to that does not have one, that I always am trying to promote in videos and so on, but a lot of people don't seem to care about this, mostly because it's a very obscure galaxy, is this one. This is the nearby galaxy known as Triangulum, Messier 33. It's actually almost right next to Andromeda. It's basically the Andromeda's neighbor. Nobody wants to talk about this galaxy for some reason or another, even though it's really cool, and it does not have a black hole in the middle, or doesn't seem to have one. If there is one, it's really small. It's just practically invisible. It has to be under like a few thousand masses of the sun. So this is one example where black hole is not required. And there you have it. Next. Thank you very much. Thank you, Ricky Morrow, for a nice comment. Thank you for wishing me a good week. Same to you. What about Planet 9 and Anunnaki? Anunnaki, isn't that? I forgot what it was. There was a famous character by that name. I don't know exactly what you're referring to here, though. Planet 9, still a big hypothesis. I don't think we're getting any closer to finding it. And more studies seem to suggest otherwise. And I'm sort of leaning toward that as well, that it might be just an anomaly of some sort in terms of data, or something might have happened to our solar system a while ago that shifted certain objects. I don't know. Nobody knows. They've explored a huge amount of night skies already, and nothing has been found so far. Have I made a video about black hole cosmology theory? Is a specific theory? Not really, but in regards to black hole formation and so on, there are quite a lot of videos about this under the playlist called Black Holes. A lot of some of the first videos were actually all about different theories. Nowadays, I'm mostly focused on specific research because I just want to know what people discovered in the last few years, just to kind of get a clearer picture on what's going on with the universe. Do you think feathering in galaxies is an effect caused by black holes? So, just to clarify this for those of you that don't know, a lot of galaxies seem to have these feathers. That's not what I was looking for. These are actual feathers. Okay, let me find one. There was a paper not so long ago that actually found a feather inside our own galaxy. It's not here. Anyway, so galactic feathers. Let me see if I can find one here. They actually look pretty cool. And the thing is, nobody really knows how they're made, but they seem to be a result of some kind of a gravitational instability, or possibly also, once again, some kind of a magnetic interaction. Here's a famous galaxy with a lot of feathers in it. Oops, here we go. This is a galaxy known as, oh, I forgot. I knew that. It is, let me look it up. It is a galaxy known as NGC 2775. No name of any kind. 67 million light years away from us. And it has these like features everywhere that kind of look like feathers inside the galactic arm. Now, these are also known as the flocculent spiral arms. And honestly, at the moment, there's really more speculation than any actual concrete answers about what forms them. But our galaxy seems to have them. And so we might actually get an answer about how they form. It does seem to relate to some kind of instability with the galactic arms than the actual black holes. So yeah, I don't know. Sorry, Tyler, if that doesn't answer your question. Okay, Coolio. What do I think about Proxima b? Do you think it has a form of life on it? Proxima b is the most interesting exoplanet we have so far. And it's the planet that most scientists are super interested about, or in, one of those. However, it's still around an extremely active red dwarf star. One of the most active so-called flare stars. Proxima Centauri is a flare star. Basically, it flares up once in a while with such a tremendous power that, in theory, it can actually strip a planet of its atmosphere in just a few thousand years. And that is a huge problem for that planet. So there's a bit of a sort of, I guess, kind of a conflict of theories. On the one side, we have scientists that think there are maybe ways for the planet to survive and be habitable long term. But on the much larger side, we have the star that seems to be just so powerful and so insanely energetic that it's basically not a good sign for anything trying to survive there. On the other hand, on the dark side of the planet, or the far side, so the planet is most likely tidally locked. It's always sort of facing the same way toward the star. The dark side, which is permanently dark and also away from the star, has a chance of maybe having something because it's not affected by a lot of radiation. So maybe. I mean, it's the most interesting planet, though. Definitely the most interesting exoplanet. Okay, Mark was asking, from the picture, it looks like the black hole is tilted. Yeah, so they did mention it seems to be sort of almost face on toward us. I'm definitely going to look this up and come back and talk about this in a future video. That is a mystery right now. What exactly is happening with our own black hole is a mystery. But I would love to know the answer to that as well. Stay tuned, subscribe, and so on and so forth. Thank you for joining, Santiago, and bye-bye as well. Okay, what do we have? Do they plan on looking at Sagittarius with James Webb? Not really, because James Webb, remember, James Webb is much smaller in terms of size of the mirror, and it's an infrared telescope. There is very unlikely to be a lot of infrared radiation coming from this region. And in terms of the visual spectrum, we've already had so many pictures from that region. They're not particularly interesting. So yeah, very likely no. But maybe, but probably no. Okay. Is Hawking radiation captured by the Event Horizon telescope while observing a black hole? So no, because Hawking radiation has never been detected by anything. It's still very, very speculative. It's only been detected via so-called analog black holes. Basically, when you create a black hole using, for example, sound waves, you create a kind of a structure where you have sound waves kind of acting like a light, and then you have a black hole that sort of absorbs the sound. In that sense, in those conditions, scientists have been able to discover the analog Hawking radiation and confirm that it exists. The real ones have never been found. And so we don't really know if it's, what it happens there, if it's sort of absorbed, or if it's emitted, or if it's interacts with anything, what it does. It's very, very, very theoretical. So yeah. What does a shadow of a black hole mean? Okay. So I think I may be able to find an image that explains this better than I can. And I think it's from NASA. It's basically the region after the event horizon where a lot of light doesn't really escape anymore. It's sort of, okay, oh, here we go. I think it's this. Let me see if this is the one I'm looking for. Yeah, here we go. So it's this. So the event horizon is like somewhere right here-ish. And then there's still a region past that where the light can, in theory, actually orbit inside this, or it doesn't have to be light. It can be a very fast-moving particle. But for the most part, the light sort of gets stuck here. And then we also have the photon ring where, in theory, well, this is where it actually says it here. Let me just read it out loud. It's a ring of light composed of multiple distorted images of the disk, and the light making up these images has orbited the black hole 2, 3, or even more times before escaping to us. And they become thinner and fainter the closer to the black hole they get. So this is the light that came from, or didn't come from, but almost came into the shadow of the black hole, but ended up orbiting a little bit and then escaping. So in theory, this is actually the most interesting part here, because this literally shows us the entire universe around the black hole. And if you could somehow capture this and then reconstruct this using, I guess, some kind of a algorithm, you could see a three-dimensional image of the universe around you. And in essence, this is basically the region that scientists are most fascinated about. I keep confusing prepositions. That's what you get for living in a country where they don't speak English for so long. You start forgetting the language. And so anyway, so yeah, that's the region that's right after the shadow, and that's the region that's a lot more interesting. Hopefully that explains it over there. Okay, next question. Do you have a favorite theoretical object? That's actually a great question. I used to have so many. What would be the most favorite now? Right now, I think I'm really fascinated with magnetars because they seem to have uncovered so many more mysteries than solved problems. Like, for example, a lot of the stuff we're seeing from around the universe, fast radio bursts, a lot of different magnetic effects, a lot of different gamma ray emissions, a lot of them seem to be coming from magnetars, and nobody can explain why. And so they are definitely the most fascinating objects. Also, some of the pulsars that tend to create very extreme environments. So, yeah. Okay. Scientists are scientists no matter what. Yeah, I agree with that. What if Mars was the size of Earth? Well, then it would be a big Mars, right? I don't know. I mean, I used to make a lot of what if videos, but then I started making a lot of mistakes in them, mostly because you have to really think a lot of things through when you're making those videos, because we change a size of a planet, right? But then what about the composition? Does the composition change as well? Mars has very different composition, so it's not really going to turn into Earth. And so, yeah, there are a lot of things you have to think through, and and so in that sense, I don't know. Did we ever image a photon ring? No, never. I don't think we have. It would be very, very difficult. But there are definitely signs of photon rings out there. Oh, wait, maybe we have. I'm thinking of that study that tried to simulate it. I don't think they actually... So they had proofs of photon ring. Yeah, okay, I'm wrong, sorry. There was a paper from about a year ago where they managed to capture light that seems to have come from photon ring because it was exactly the same emissions of exactly the same photons, but they came at different times, suggesting that they must have traveled around the black hole a few times. So that was basically a detection of the photon ring around the massive black hole. So yeah, we have. Sorry. Oh, okay, someone else is asking if they showed anything. And those of you who are just joining us in for the first time ever, here we go. Be absolutely, okay, curb your enthusiasm first of all, but be absolutely surprised and shocked by this. This is the image of the Sagittarius A-star black hole in the middle of our own galaxy. And yes, I know that you're about to say it looks like a potato picture, and that's because of the difficulty of taking these photos, pictures, images. Okay. Can we make a Dyson sphere around Proxima Centauri? Why would you want to do that? It's so much work. Why Dyson sphere? I think we should start with the, geothermal energy. That's where it's at. Start digging, creating a lot of geothermal energy that starts producing free energy for everyone. Oh, okay. Corey is asking a clarification about when you said black hole is not required. What did you mean? In a typical galaxy, black hole could originally have been there. It could have been sort of the center of the original center of the black hole, basically the core of the black hole. Sorry, not the black hole, galaxy, core of the galaxy. But in theory, they can actually get kicked out through a collision process, for example. And in other theories, you can also technically create a kind of a formation that resembles a core of a galaxy without a use of a black hole. So there are some galaxies out there where the black hole is absolutely not required. The galaxy can exist without a central black hole, which we know many of, or several. There are several galaxies that don't have any black holes. But most galaxies seem to have them. So in that sense, scientists, I think, believe that they must have all had it and some of them just lost it, maybe. So yeah. Will humans still be around in 5,000 years? Yeah, very likely. I don't know what sort of a civilization we're going to have, but there is no reason to believe that humans are going to go extinct, even if conditions worsen dramatically. Not only do we have an extremely resilient species, but generally speaking, you need to have another species cause the extinction of us in order for this to happen, and that just doesn't exist right now. So yeah, unlikely. We're going to be around for sure. Yeah, I use a different mic for this stream, and also my voice is just destroyed by the amount of pollen in the air. I have really bad allergies to certain types of what do they call it? Basically, a kind of a cedar tree that grows in South Korea, and my voice just goes sideways when it happens. I do need to get a better microphone though. Thank you for the donation to the Save the Children. Highly appreciate it. Thank you, Raven Looney. Okay, so here we go. What did I miss? Can a black hole eat dark matter? I mean, this is a very hypothetical question because we don't really know what dark matter is, to be honest. And the more studies we have, the more likely we seem to be discovering that it seems to be something that we just don't understand at all. It could be just an effect of something else. So far, it does not seem to be a particle, but even though that used to be a prevalent theory, nobody knows what dark matter is. We only see the effects, that's the thing. We only see that, something is causing galaxies to sort of stick together. Something is causing a lot of gravitational lensing effects in certain regions. But what is it? Nobody knows. Okay, do we know? Oh, I missed it. Where is it? Do we know black hole jets fall or are related to its axis of spin? So generally speaking, that's what's believed today, that if you have the accretion disk spinning this way, that's how you will most likely have your magnetic lines. I have a very sort of simple simulation of this here. Hopefully you can see this. Here we go. So the magnetic lines of a black hole might sort of resemble this. And so the accretion disks, the astrophysical jets, come back video. Where did you go? The astrophysical jets, in theory, should be pointing this way. So that's kind of what the scientists think happens. But that's only from the last few years. I mean, that's just very theoretical. Nobody really knows what's going on, and I don't know what's going on even more. What academic background do you have? Mostly in education, to be honest. I've always wanted to be a teacher, and I kind of got disillusioned with a typical school environment. I'm still teaching, just not full time. And my problem was really with the fact that most schools today completely refuse to change their curriculum or their approach to teaching students. And when I was teaching math, I was a math teacher for about 8 years. I was just filled with so much, I don't want to say apathy. It's more of a sadness, I guess. It's just teaching students for the test, teaching them how to pass the test as opposed to teaching them the beauty of math and trying to explain how things work and trying to explain the concepts. And that's how, to some extent, this channel was born. I started with math videos, and eventually I just kind of went into other directions that I really enjoy talking about. So most of it is just self-taught. Academically, I'm a horrible student, and I've never really done well at school. But I like teaching. What university did I go to? I graduated from McGill University in Montreal a long time ago. And that's actually the university where I met someone who kind of gave me a spark of interest in astrophysics. There was this Iranian professor, Professor Hachatollah Vali. He was one of the guys who actually was originally trying to argue against the what was it called? The Martian meteorite where they thought they found life, ALH 84001. So he was one of the but I guess one of the major researchers that was trying to argue that, that meteorite from Mars that Bill Clinton mentioned, this thing here. He said, this is not life, guys. This is not life. I can prove it. And so for many years, he was trying to find evidence of other stuff. And that was actually, I remember one of my earlier part-time jobs in his lab was basically grinding rocks for like a few days, trying to figure out how all of this works and trying to grind meteorites and find particles in them and trying to see if we can find or not find something that looks like life. And I had no idea what I was doing, but it was so much fun because he was mostly a very positive person. He inspired me to, keep looking by myself, ignore professors, teachers, just keep looking, focus on what you want to learn about and just do your best to find the answers. And that was a good attitude. Although he wasn't obviously perfect, he used to get really mad at me when I would screw up. He would just have these anger issues once in a while, but I love the guy. He was great. I think he's retired now, though. He's pretty old. Okay, so those of you who are just coming in, who missed the big announcement, here you go, 3, 2, 1. This is it. The Sagittarius A Black Hole image released by Event Horizon Telescope just a few hours? Yeah, a few hours ago, a couple hours ago. So people are asking me if I'm Ukrainian or Russian. So my family is from both countries, and I'm not going to get into politics, but I feel like I lost a huge part of my Russian family now because it's just impossible to communicate on the same level. And whereas for my Ukrainian family, they're just living in such misery. It's really sad. I mean, I've tried to help the best I could, but and I'm talking about a quite extended family. My mom immigrated to Canada when I was really young, so I don't have much connection to either countries. But I try to connect to them, I try to connect culturally, but it's difficult. It's because, if you're a child growing up in French Canada, where there are a lot of immigrants to begin with, you kind of have a different mentality. And, where you have more open mind to some extent. Whereas a lot of people in Eastern Europe, for example, they'll have a slightly different approach to life. So it was very difficult to communicate with a lot of the people I tried to reach out to in the last couple of months. I'm going to try to take it easy and maybe just let the time heal the wounds, at least for my family. Because, the Ukrainian side and the Russian side, they're just, there's so much hatred going on right now. It's very, very sad. Okay. Okay, so someone is mentioning that I have talent for teaching. So this is the thing. I don't actually believe talent exists. It's not a thing. You have skills, right? Your skills that you develop. If you ever watch my first few videos, they're horrible. Like, I would never want to watch them because they're just, I have no idea what I'm doing. With time, though, you realize, how to maybe explain things, how to not explain things, and more importantly, you realize what people don't understand. And that's the question you should be asking yourself when you're teaching. What do your students, whoever you're talking to, your audience, even if you're a presenter, not understand? Do they not understand this concept? Or are they going to be able to understand everything I'm saying? And so it's very, very, very important. Okay, cool story. All right, let's see if there are any science questions. Please stick with the science questions, no politics or anything. Anything significant about the black hole other than being in the center of the Milky Way? Well, I mean, so here's the thing. No, the answer is no. But when you think about it, we've only really confirmed this to be a thing only 2 decades ago. Like, so let me go back to that image from before. Not this, not that. Here we go. This is the. So these are actual images taken by actual telescopes over a period of approximately just under 20 years. And this is the motion of different stars around something invisible in the middle. I believe Andrea Getz, who won the Nobel Prize in 2020 for this, was one of the main investigators creating this. And so, the fact that we confirmed the existence of the black hole and now we have a picture of it, or we have this of it, is a huge deal in terms of achievements. And so this is how it starts. Now they'll be collecting more data. They'll be trying to figure out what they got wrong. If they got anything wrong, they'll be trying to figure out if there's a lot of polarization around the black hole, if there's a lot of different types of activity that M87 doesn't have. Altogether, all of the stuff is going to create a kind of a more wholesome understanding of what we think black holes are, especially central black holes. And more importantly, it's going to create, hopefully a new generation of people just wanting to go and explore this by themselves. Like, maybe someone watching this right now is going to go like, oh, wow, this is actually pretty cool. Like, why don't I just go and study this and become the next Stephen Hawking? So there's a bit of everything in there. So it is cool. It's not anything super groundbreaking in terms of scientific discoveries. It's more groundbreaking in terms of, I guess, science communication. It's an absolutely groundbreaking science communication discovery. So yeah, it's cool. I love it. I mean, even though the quality is kind of as bad as I expected it to be, it's cool. And yes, some of you who are late to the live stream, yes, this is the image of the black hole, the new image that was just released. So yeah. How big is the Andromeda Galaxy central black hole supposed to be? I don't remember the exact number, but it's a little bit more massive than the one in the middle of Sagittarius A. Just a little bit bigger, not by much. So they're kind of similar in that sense. Oh, I love you too, all of you. Okay. So what else do we have? Okay, looking for more science questions. Next up, TON 618. Yeah, so the TON 618, you might know about this one. It's one of the biggest black holes we've discovered. It is, though, really, really far away. It will be practically impossible to take a picture of that. So, yeah. What is the biggest discovery confirmation we will get with James Webb Telescope? I think, this year, I think the biggest one is just going to be the sheer number of galaxies we're going to be seeing coming from, like, billions of light years away from us. But in terms of confirmation, I'm not sure. I have to think about it. It's not a question that I can answer right away. Definitely some confirmations in regards to exoplanets, especially their atmosphere. It's going to be able to analyze certain atmospheres very well. And so discovering certain molecules in even that Proxima b we discussed not so long ago would be a big deal. Discovering, what sort of stuff is in the atmosphere of that planet. That's probably going to be one of the bigger discoveries in the next few years. So someone is asking that question about the 3 bright objects here. Those are not stars. Those are very likely flare ring. Okay, so one, I'm not sure. Two, I think it's the flares from different emissions around the accretion disk that were created when they combined all of the images together. So this is not just one single image. This is a kind of a statistical representation of thousands of different images together, because it was very difficult to take a picture of this black hole just this one time. And so they combined various recreations and created a kind of overall average of everything. And it looks like this. And it has these three bright parts, which I believe are just flares. Or maybe, no, it's probably not I don't think it's related to Einsteinian ideas. Yeah, it has to be some kind of a flaring from the black hole, from the accretion disk. I don't know. Well, come back and I'll let you know in a few days when I read their papers. They haven't released anything yet, or if they have, I haven't read it yet. It was all just announced 2 hours ago. So, and unfortunately, here's the thing. I'm surprised nobody asked the question during the stream that they were doing, and so we don't know. Nobody knows. Yeah, so with M87, we did see that one bright spot, but remember, M87, the stuff around it moves much, much slower, so it's much easier to capture the more accurate image. With Sagittarius A, the problem is that stuff moves like hundreds, thousands of times faster, so it's just basically a lot blurrier. What do I think about TRAPPIST system? I've just finished making a video that mentions it briefly, but it's an interesting system, but it's very likely not habitable, very likely. The reasons you'll learn about in the video, but it's related to the age of the planets in the system. They're just too old. Are there any ongoing projects that will allow us to image other regions of the Milky Way hidden from us because of the location, like Sagittarius A star? I mean, I can't really think of any specific project, but there are several surveys that are constantly ongoing, including the Gaia telescope, for example, that are actively looking at various regions, and then using the data, some scientists will be able to recreate certain regions we cannot see otherwise. But I can't think of any specific project that's looking for anything specific. It always usually comes, as some kind of a paper where someone collected data, or someone used the data that was already collected years ago, and then they would actually find something hidden somewhere. It's very, very rare that you'll have like an actual project looking at a dark region or somewhere unknown. Okay. Yeah, so someone mentioned that maybe these spots are Doppler effects, Doppler boosting, and that's what I thought initially, but it's just hard to explain the Doppler boosting effect on the top part. How would you explain that? Unless this came to me, unless the disk is actually not a disk. If it's a ripple, maybe it's a ripple disk. Oh, that reminds me of another video I just made. So there was a black hole recently discovered that actually has a very strange disk. I'm just going to see if I can find a picture of it, or a illustration of the black hole. So there's this strange black hole that has a disk that's inclined. It's an inclined black hole with a disk that's about 40 degrees inclination to the jets. Now, nobody knows why. It was just discovered like 2-3 weeks ago, maybe a month ago. And maybe that's what's happening, maybe. But also maybe not. A lot of speculations on my part. Don't take anything of this seriously yet, because we'll have to read the papers. My apologies. Okay. Oh, my voice. Okay. What else do I have? Can ripples in space-time move celestial bodies? I'm not sure what that question means. I'm sorry. You mean gravitational waves? Can the gravitational waves move celestial bodies? Yeah, in theory they can, but it is well, yeah, it's not to the point where they would be like surfing the gravitational wave, although that's kind of possible too. But yeah, sorry, I'm not sure what the question is. But yeah, in theory, gravitational waves, if they're close to a physical object, could move that object away from a certain location. I mean, that's kind of what, if you look at LIGO, the detector of gravitational waves, that's kind of how it works. Because the gravitational waves that come to us from, millions, billions of light years away, they actually move the space-time. You don't feel it, but they move it, they sort of shift it around. And by shifting the space-time, by contracting our planet just a little bit, we can see this by using these very powerful lasers. So maybe that answers the question, maybe? I don't know. What else did I miss? Can Webb show us UI Scuti? In theory, yes, but as you might have learned from the video from a few months ago, UI Scuti is no longer the biggest star, so it doesn't really matter anymore. There was a miscalculation in terms of distances, so it's actually way, way smaller than anyone thought. And it's not even like in top 10 anymore. Or maybe it is. No, I don't think it is. So, but yeah, in theory it could. UI Scuti used to be one of the biggest stars ever. Or actually was a record holder at some point. Okay. Okay, so people are asking about dark matter questions. In terms of dark matter, it's hard to answer those questions, mostly because we have no clear idea what it is. We don't know if it's inside black holes, if it's there, if it exists. We know that there are effects that we refer to as dark matter, but it could be not actual physical matter. Nobody knows what it is. It hasn't been discovered. It could be just misinterpretation of gravitational formula as proposed by the Mond theory, but also maybe not. But all ideas we have right now about dark matter is simply based on observations from around the universe. So it's just an effect. It's not an actual physical matter, at least not yet. Nobody found it. Okay. Can galaxies form without a black hole? So the simulations that the scientists ran before did not require black holes to form galaxies, but going back to my previous comment, they did require hypothetical dark matter. As a matter of fact, pun. Let me use the video that I use sometimes. This is from the iconic Illustris project. Such a difficult name to pronounce when you're tired. And the thing about this project is that it's been able to recreate a lot of stuff we see around the universe using supercomputers. And one of the things it recreated sort of looks like this. Where is this thing? Yeah, here we go. Can I show you this? Maybe. Okay. Why is it so small? Anyway, so this is the so-called cosmic web, and it's believed that this cosmic web is basically everywhere. It's actually been proven many, many times. It's been seen by many different telescopes. Inside this cosmic web is a higher density of matter, galaxies, stars, and hypothetical dark matter, which most likely served as a kind of a foundation / building block of the web itself. And so you don't need black holes, but you seem to require higher concentration of dark matter to form this formation that seemed to be everywhere in the universe. And as someone else asked like an hour ago about Boote's void, there was a question about, what do I think about Boote's void? Well, not much, because if you look here, you'll see that there are voids everywhere. Boote's void is just one of them. So the voids between the web itself, maybe it's a little bit easier to see if I show you this video actually. Also from the iconic Illustris project. Okay, here we go. So this is during the early formation of the universe. You'll have galaxies, and then you'll have these voids everywhere. And so these voids are sort of formed. Here, this is an even better one. Sort of formed. So these large voids sort of formed by having a little bit less dense stuff in there compared to, actual cosmic web. And so, in conclusion, where was I going with that? Dark matter could be real, but we don't know what it is. It might have formed cosmic web, maybe. Cosmic web is real. It has been seen several times. And very recently, I haven't talked about this yet. I'm not sure if I will. But the very powerful radio telescope in Canada and in BC, the telescope known as CHIME or CHIME, I don't know how to pronounce it. It's CHIME. that telescope recently was able to identify potentially a part of cosmic web a few billion light years away from us by looking at the radio emissions of hydrogen coming from the region. So yeah, it's very likely there. And so in that sense, let's play some music before I finish the stream. I'm going to take 10 more minutes before I finish this. In the new image, how wide is the ring in light years? Oh, that's a great question. Oh, I wish someone asked it during the stream. So this is, I don't think it's in light years, to be honest. It would have to be most likely in astronomical units. I would say it's solar system sized, but this is a huge guess. I would really have to look at this. They did present data during the stream, but it wasn't very clear in terms of size. And I'm going to have to come back to you. I'm going to be making a video about this where we're going to be answering these questions. But yeah, I would have to say it's not even close to a light year. It's probably way smaller than that. Okay. Next caller. What kind of music do you like? I mean, I like a lot of stuff, but usually, especially nowadays, I just listen to stuff you hear in the background right now. Just something calm. Something that makes things a little bit easier on the ear. Would an inclined disk around the center suggest a recent merger? That actually, yes, that's actually maybe one of the reasons why it would have an inclined disk, or it could be some kind of a strange astrophysical effect we don't understand yet, but particularly effect related to maybe the spin of the black hole. But yeah, there's a high chance that collision or a interaction with a large black hole could have caused that. Cool. And next, what else do we have? Okay. Can a black hole disappear sometime after long term? I mean, in theory, black holes are supposed to disappear according to Stephen Hawking. That's what we refer to as Hawking radiation. But it's extremely theoretical at the moment, and nobody really knows if they really do because it cannot be tested right now. So there. All right, let's gonna take 3 more questions, and then I'm gonna have to go to bed soon. Mostly because at around 8:30 a.m. my son is going to be waking me up and asking me to take him to his favorite kindergarten. And I'm gonna be super tired, and I'm going to have to stay awake. If I stay awake, that is. So yeah. During this stream, they said the shadow is as big as Mercury's orbit around the sun. Oh, they did? Oh, I missed that part. Huh. Okay, so if this is as big as Mercury, then the disk itself is going to be maybe just a little bit past orbit of Venus? Maybe close to orbit of Earth? Okay, interesting. I missed that part. I totally missed that. Thank you, who mentioned that? Someone just mentioned that. I missed the Eduardo, thank you. All right. Could aliens be involved somehow? No, not really. Not really. Some people are telling me good night, and some people are telling me no sleep. Is James Webb too sensitive to look at black holes? No, it's not. It's not that it's too sensitive. It's just not the same frequency. Also, there's, if you look at this again, there's no infrared stuff coming here. All of this is radio waves, so you're probably not going to see much. Most of the light, not light, I guess it is light. Most of the stuff we see from typical black holes, which I'm going to illustrate because I have so many videos saved from so many years. So all of the stuff you see here, all of this, it's either visual light, optical, a lot of UV light, a lot of X-rays, sometimes, occasionally gamma rays, but not that much infrared. A little bit, but not enough to be able to, well, I guess maybe some infrared. at the outskirts, but not enough to make a difference. But quite a lot of radio light because of the magnetic fields. So yeah. Yeah. Okay. What do you mean by black hole facing us? Yeah, I should have clarified this. So yeah, black hole is in theory a sphere, but as you see from the image, the accretion disk has sides, right? So if this is its side, then this would be face, or maybe this is the face, or I guess a butt. But so facing means that way. But they're suggesting that maybe it's almost entirely facing us. And I am disagreeing because I don't really see the evidence from other studies. But I want to read their conclusion. I actually want to see why they think so. It would be really interesting to see if they found something incredible in regards to this. Maybe it is actually spinning around for all we know. Or maybe, I don't know. It'd be interesting. Is the black hole causing the rotation of the galaxy? No, not at all. Black hole has very, very little influence on the galaxy. Very, very little. What would happen if those accretion disks were not there? I mean, those accretion disks are mostly there because there is stuff around the black hole, usually stars that are stuck there. If they were not there, it would just be like the majority of black holes out there that we can't see. It would just be invisible. There are probably black holes like only a few light years away from us. We can't, okay, not few light, I would say a few dozen light years away from us, but we cannot see them because they're still far. They're not absorbing anything, so we can't see them. Would it not look the same from every side? Not necessarily. So, oh, the space engine will leave the chat. Oh, I was going to use Space Engine to illustrate this. Space Engine is the team behind Space Engine, the app I use a lot. In that app, you can actually... Can I open this right now? Maybe I can open it. It might. I hope it doesn't crash my thing. And yes, I do need sleep. So I am going to bed very soon. You can't stop me. I guess you could, but don't. Let me just show you this because this is sort of important to illustrate. If I can open it without crashing the stream, sometimes it crashes stuff. Not the Space Engine, but just my computer. Okay, here we go. I wonder if you can actually see everything I see. All right, let's go to the Sagittarius A star simulation. Remember, this is a simulation based on what we know about the black hole. And here, if we... wait, oh, okay, I might as well just go manually. Okay, here it is. Oh, wait, slow down. Okay, so there is that black hole, right? Hopefully it's not too bright. Let's dim it a little bit. Okay. Now, it might look like this, right? Well, that's what we thought at least. But the image seems to suggest, once again, let's dim it a little bit. The image they released seems to suggest that, it's like maybe that way. Like sort of this way, at least. Or maybe even this way. But not exactly like that. It's sort of like here. So it does look different because you actually, despite the effects from not astrophysical just, but the accretion disk, you're still going to see the disk itself. The disk doesn't orbit everywhere. It's not a sphere. It's more disk shaped. And so here, this is what they're suggesting. But the thing is, previous studies from just a few months ago did find signs of jets that are pointed this way from just a few thousand years ago. So what's happening? Nobody knows. It's a mystery. It's a mystery that only science can solve. And we'll probably know soon, but I don't know. Maybe there was a miscommunication somewhere. That's what I would love to find out. Okay, someone is saying don't buy Space Engine. Yes, you should buy Space Engine for one simple reason. It supports the team that's been actually doing this for years absolutely for free. And I do highly suggest or recommend supporting them because they've done a great job for science communication. Space Engine is actually created by, well, there's at least a few astronomers and astrophysicists working behind it from what I remember. But yeah, they deserve our money. It's only $30, come on. But yeah, I'm totally not part of the team or anything like that. I've just been supporting them for a long time, several years. Oh, okay, so I can hear my computer is struggling with this. And also my stream is slowing down because of this. I'm gonna have to close this. It's usually because of the graphics card that it starts lagging quite a lot, and everything, including the video, started lagging. Did they show the breakthrough yet? So in case you missed it, here you go. This is the image that they've been talking about for the past couple of hours. Maybe not as impressive as some people expected, but very impressive for what they were working with and what they had to create using the data that they had. Is there evidence to suggest black holes can wobble like magnetars? Well, I mean, yeah, like that black hole I just showed you previously, which did I already close it? That had the inclined accretion disk. One of the more reasonable explanations is that there's some kind of a wobble going on because of something. So yeah, maybe. But also no specific proof just yet. Okay, cool. Ton 618 is probably not going to be imaged anytime soon because it's just way too far. It's just ridiculously far away. So yeah. Okay. And maybe a couple more questions and then I go. Getting super tired. What are the bright areas in the picture? So yeah, as I mentioned before, currently we don't really know, but I think it's the flares from the accretion disk. And because the image was combined with other images, it just looks that way. And okay, cool. Thank you very much for all the support. I love you too. Any comment gravitational waves hitting our system? Any gravitational waves hitting our system right now? Well, you can actually check that. Usually all of this data is publicly available and up to date on the, what is it called? Oh, Jesus. Grace. Is it called Grace? Yes, Grace. Grace? Where is Grace? Is this Grace? Grace is a database by oh no, that's not it. That's not the right Grace. Oh, okay, I forgot what it is. I forgot the website. So anyway, it's a report that shows all of the gravitational waves detected as of, I guess, recently. But at the moment, I don't think there was anything major reported. So yeah. What algorithm did they use for data processing? I have no idea. They did report their algorithm in the previous M87 detection, so I'm guessing something similar. But from what I remember, it was ridiculously complex. I mean, I sometimes think I'm good at math and programming because I've done it for many years. And I looked at it, opened the actual report, and I decided to just close it and go to bed because it was way above my pay grade. It's just ridiculous. I mean, if I had spent maybe a few days studying it, I would probably figure it out. But at that moment, it was not as crucial. Okay, cool. And maybe one last comment, question, or concern. Okay, I'm trying to find something else. Okay, cool. Oh, yeah, well, I should be showing you image more than anything else. So this is the image that was being shown. And thank you so much for everything, really. Are there any radio frequency emissions from the black hole? So this is all radio frequency. Everything you see here was created in radio frequencies. This was made with radio telescopes. There's no other frequencies here. This is not optical light. This is not what the actual black hole looks like in optical light. This is what it looks like in radio waves, to some extent. And so therefore, that is maybe all I'm going to say today. And also maybe you should be subscribing if you still haven't. And maybe also, you know that donation box somewhere right there? Oh, it used to be there. Uh-oh, did I remove it? Oh. So yeah, the money donated goes to the Save the Children Foundation. And a lot of the stuff is actually going to be going to kids of conflict, and specifically Ukraine, but also different other countries supporting refugees and supporting kids around the planet. I've been personally discussing this with them, and they do a tremendous job. They actually are probably some of the better charities I've worked with in the past, and I'm so glad we've raised so much money. I'm super grateful to everyone who donated through Patreon, through PayPal, through the channel membership, pretty much with some exception of maybe a few dollars that I used for, I think I bought a subscription to one of the video channels, providing thingies that I use, like the videos that you always see. This stuff, all of this I have to pay for. So that was the only money I used from everything that has been donated in the last few months. And honestly, I just feel guilty about a lot of things that happened in the last few months, and also feel extremely saddened, especially as a parent who lost a child. I feel very saddened by what many parents go through right now. And so that's why this particular drive exists, and that's why I've been doing this for a couple of months now. I'm probably going to be finishing it officially in maybe, I would say, a few weeks from now. But I'm going to be putting a huge chunk of donations into that big chunk that I've collected from other people as well, from personal donations from my friends and family, and from a few people I know. And so eventually we're hoping to raise maybe $200,000, and all of this will go to help those kids. But even if you can donate, just you being here, and the fact that this is being watched and the YouTube is going to be promoting this, hopefully through the fact that YouTube is going to be paying me for this video at some point, I hope, unless they tag it as conflict video, this is also going to them as well. It's just, it's a time when I feel like it's very difficult for me to think about anything else except for what's going on in Europe, and also what's going on with my own family, to be honest, my extended family. But on that note, I don't want to end this on a sad note. I'm very grateful for all the support over the years, and I'm still cannot believe that there are a million people that want to watch this stuff. But hopefully I keep going and keep making this and keep doing this. And in some of the future videos, once my son grows up a little bit and starts talking a little bit better, he's maybe going to come and join the stream and maybe ask some other questions and talk to you people. You people sounds horrible. To you wonderful people. You wonderful individuals all over the world. Anyway, so thank you so much. I'm super tired now. I'm starting to ramble, and my tongue is not in the same condition as it used to be. And also because of the, basically because of the allergy I've been suffering from for the past few weeks. Tomorrow, I think I'm probably going to skip the video, mostly because, well, a lot of people will probably be rewatching the stream. And on Saturday, we're going to be talking about something else. I don't think I'll be able to make a video about Sagittarius A-star just yet, because I really want to look for all of the data they've collected and read all of the papers they have, or at least try to skim through them to some extent, and they're going to be super long. And just, see what we can find about those answers. Like, what are those spots? What is going on here? Is it really facing us? And if not, what's happening? So those are really good questions, and nobody really knows the answers to yet, because during the Q&A session, unfortunately, the answers were not very clear. And I feel like a lot of people were maybe not happy with the answers. And it's not because they didn't know, it's because, science communication is difficult. So give them a break. On that note, stay wonderful. Most importantly, stay positive. Don't do anything bad, horrible. The world is already full of that, so we don't need more of that. And enjoy, learning about science. Enjoy learning about the universe, because there's just so much incredible stuff to discover. So why wouldn't you, right? Why would you do anything bad when there's so much great stuff out there? And so on that note, I will hopefully see you very soon. And as I mentioned before, the streams, I've been trying to make this a regular thing, but something always comes up. So I'm going to try. I really need to try, because I've promised so many subscribers, and especially YouTube subscribers, that I'm going to start doing this regularly. We're going to hopefully have another stream very soon. I'm hopefully going to get rid of this microphone and get a better one. And everything hopefully will get better soon. And so on and so forth. On that note, anything else I need to mention? No? Stay wonderful. I will see you very soon. And as always, bye-bye. Okay. Anything else? Anything important? I'm trying to see if there are any super important questions I missed. Thank you for the donations, anyone who I missed. And I love you so much. Okay, bye-bye. Really, I need to go. My son is going to be very, very persistent, waking me up tomorrow. And I'm going to be super, super tired. And therefore,